are finally on the last question, question 10. So question 10 says, 10.1, flags from 4 African countries and 3 European countries were displayed in a row during the 2021 Olympics. Okay, so determine the total number of possible ways in which all 7 flags from these countries could be displayed. Okay, so all we're just thinking about is that there are a total of 7 flags. Okay, so 4 of them are African. So just say this is a flag, and we're just going to have these 7 flags. And so we have 4 African flags. I'm just going to say African flag 1, 2, 3, and 4. And then the European flag. So 1, European 2, and European flag 3. Okay, so this is what we have. They just want the total number of ways that they can represent these 7 flags. Okay, so what are the total number of ways? All we're just going to have to think about is the fact that there are 7 flags. So you're looking at it like this. The first flag, when we have to display the first flag can either sit in this first position, it can sit in the second, the third, the fourth, the fifth, sixth, or the seventh. Okay, so the first flag has 7 options or 7 choices to be placed in. Then after the first flag has been placed down, the second flag, how much more options does the second flag have? Because the first flag has already been put down, the second flag will only have 6 more positions to be put in. So it can either be put here or here or here or here or here. So that is times 6. After the second flag has been placed down, wherever it's going to be placed, the third flag now, how much more options does, or how much more places does the third flag have to be placed in? The third flag will have only 5 places, here, 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 or here. Okay, so that is 5 places. And this is really how we keep going. The fourth flag will have how many more options to be placed in? 4 more options. The fifth flag will have how many more options, how many more places to be placed in? Only 3 spaces, here, here, or here. That's 3 places. Then the sixth flag will have only 2 options. And the 7th flag will have only 1 option since everything else has been placed. And that's how we look at that. So on your calculator, this is really just 7 factorial. So you can go ahead and say 7 factorial and let's see what we get. So on your calculator, you're just going to say 7 and then shift and this button for factorial. So that gives us 5,040 ways. They can be displayed in 5,040 ways. Okay, moving on to the next question. Question 10.1.2 now says the probability that, so we have to determine the probability that the flags from the African countries were displayed next to each other. So we are only placing the flags from the African countries next to each other. Okay, so these are the flags that we have. I'm just going to put them here and we're going to group the flags from the African countries next to each other. So it means that we have created a group. This group is only African countries. Okay, so that's the only group they created. They never said anything about the European flags now have to be placed next to each other. So a common mistake is when they make something like this, when they say something like this, where they say that, like for example, African countries need to be next to each other, people may just immediately assume, okay, so if the African flags are next to each other, then by default, the European flags are next to each other. But that's not true, because look at what can happen. You see, they are next to each other. But this European flag, for example, can sit in front of the African flags. It's possible. And it could even be a case where 2 European flags are sitting even in front of the African flags, as long as the African flags are sitting next to each other. Okay, so this is the way that I like to work through questions like this. I'm going to identify the groups that have been formed. So the first group we have here is the fact that the African flags are placed next to each other. So despite the fact that they are placed next to each other, we still have to look at the total ways that they can even be seated or be displayed like this, even as a group. The reason why is because, for example, this first flag, remember they're all different flags, they're not the same flag. This first flag doesn't have to necessarily sit in this position. This first flag can even be seated in between 2 and 3. And the first flag can even be seated here. So to find out the total number of ways that these flags as a group can be displayed, we have to say 4 factorial, because there are 4 flags in here and we're looking at the number of ways that the first flag can be displayed in this group. The first flag can either sit in the first position or sit in the second or the third or the fourth position. But after this first flag has been placed down wherever it is, the second flag will only have 3 more options to sit at. And then the third flag will have only 2 more options to sit at because the second flag is seated. And then the last flag will only have 1 more option. That's why it is 4 factorial, because that's really 4 options times 3 options times 2 times 1. That's where that 4 factorial is coming from. Okay, so that's how I like to view it, as I'm going to group them together like that. Then these ones, they are not a group. So what I'm going to do is I kind of look at each of these as if they are a group on their own. As in, that is just one group on its own, that is one group on its own, and that's one group on its own. This part is not really necessary. It just really helps with thinking it through. So since this is one group on its own, I'm seeing it as how many ways can this flag be placed as one group on its own? Because there's only one flag in this, it will be 1 factorial. Okay, because there's only one flag in this little group over here that I've just created. And then in this one, it will be 1 factorial and 1 factorial. Okay, and what we're doing is we're multiplying all these numbers. Then the last thing we're going to do is, because we don't want it to necessarily just sit like this, what I've done right now is I've only found out the total ways that these flags can be seated. I've also found out the total ways that these flags can be seated. But the only problem with this right now is that they will only literally stay in the positions that they are. Like this group will stay here, this one would just stay here, and that one would stay like that. What I want is not that. I want these groups, these ones, to also be able to move around. I want this one to, for example, be able to sit here, or be able to even sit in between this red group and the blue. So in order to do that, now you're going to have to find out how much groups have now been created. The amount of groups being created would be this. This is one group on its own. This is another group. That's the third group, and that's the fourth group. We have created 4 groups. To allow these 4 groups to be able to be seated in any way, we're going to say times 4 factorial. You can kind of see it as if I'm treating each group as if it's now an individual flag, as if this one is an individual flag, and I'm saying, okay, this individual flag, how much options does it have to be placed in? It can either be placed here where it is in the first position, or it could be placed in this position, in this second group's position, or in the third group's position, or in the fourth group's position. So this first group has 4 options to sit at. Then once the first group is seated, I'm looking at the second group, which I'm treating as this one. So this group, how much options does it have to be displayed in? Because the first group is already seated, it has only 3 more options. It can be seated here, here, or here. So that's times 3. Then the third group has how many options left? Only 2 more places to be placed in. And then the last group, because all of them has been placed, will only have 1 more place to be seated at. So that's how I'm looking at it. And that's why I say times 4 factorial, so that these groups can also move around as if they're individual flags, and so that we don't have a situation where they have to be seated like this. Instead, this flag, for example, can be seated here, or be seated in between here, or even in between here. Okay, so that's the way I like to look at it, and it makes a lot of sense. So this is what we can do now to simplify this. You see, 1 factorial, if you check on your calculator, it's just 1. So it's like 1 times 1 times 1, which is 1. And if that 1 is being times by 4 factorial, it will just stay 4 factorial. So this is really what this simplifies to. It's 4 factorial multiplied by 4 factorial. Okay, but just remember, the question is, we have to determine the probability that the flags from African countries were displayed next to each other. The probability. Okay, so this one, what we're just finding is the total ways that the African flags can be placed or displayed next to each other. So what's 4 factorial times 4 factorial? And that is equal to 576. Okay, but then this is just the amount of ways that the African flags can be placed next to each other. We still need to find the probability. So to find that probability, that would be So the probability that the African flags would be displayed together, that would be this, the 576 ways, over the total number of ways that all the flags can be displayed without being grouped. And that was this 7 factorial. That was the total number of ways all the flags can just be displayed. So that is 5040 over 5040. Let's go ahead and see what that simplifies to. So 576 over 5040, and that's, okay, I'll leave it as a fraction, is equal to 4 over 35. And that's our answer. You can leave it as a decimal, as a percentage, it's also fine. Okay, so that is 10.1.2, and moving on to the next question. Okay, so 10.2, we have A and B are independent events. Probability of A is equal to 0.4 and probability of A or B, is equal to 0.88. Calculate the probability of B. Okay, so let's use what they told us. This is for 3 marks. Probability of A and B, that they are independent. That's what they said. There are 2 independent events. Okay, so what do we know about independent events? We know that if 2 events are independent, then the probability of A and B would be equal to the probability of A multiplied by the probability of B. That's what we know about independent events. Then they gave us information about the probability of A, but then they also gave us the probability of A or B, and they also told us to calculate now the probability of B. So we need equations that will have the probability of B in it. This equation has the probability of B, but we don't have the probability of A and B. Okay, so let's use what they told us here. They also told us about the probability of A or B. The equation for that is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, so this is definitely what they want us to do. Do you notice that we know we are looking for the probability of B, right? The probability of B are in both equations, but the probability of A and B are also in both equations. So what we can do is make the probability of A and B a subject here. It's already a subject here. Then we can equate them, and then we'll be able to say, because we will equate them basically because they will both be the equations of the probability of A and B. So what I'm going to do is I'm going to take this over to make it positive, because right now it is negative. So it's now the probability of A and B is equal to the probability of A plus the probability of B. Let me actually just fold that in. I know what the probability of A is. It's 0.4. 0.4 plus the probability of B, we don't know that. And then I'm taking this one over minus the probability of A or B. But the good thing is I know what this is as well. This has a number, 0.88. So I'm going to replace that with 0.88. So minus 0.88. Okay, so you see, you have the probability of A and B as a subject of that equation, and we have the probability of A and B as the subject of this equation. Let's just simplify this a bit more and then also fill that in. So here we have the probability of A and B is equal to, we have the probability of B. I'm going to put that first. Then what is 0.4 minus 0.88? So 0.4 minus 0.88, that, I want it as a decimal here. So that is negative 0.48. Okay, so that is the equation for the probability of A and B. We have that. Then I'm going to take this equation. Let me actually pull it down and substitute what the probability of A is. So this was using the fact that they were independent events. And the other one was, of course, using the fact that they told us the probability of A or B. So in the independent events, we're saying probability of A and B is equal to, and we know the probability of A is 0.4, so that is 0.4 multiplied by the probability of B. Now, this part is kind of like if you were saying something like 0.4 multiplied by x. That would be 0.4x. So I can just call this 0.4 probability of B. Okay, so probability of A and B is this. So now we have equations for this probability of A and B here, and we also of course have it in this one over here, so this side. What we can do is now equate them. So we can say the probability of A and B is equal to the probability of A and B. Okay, so that's that equation being equated. I keep leaving letters out. B. Okay, so that's that equation and this equation over here. So I'm going to say this one is equal to this. So probability of B minus 0.48. And this is equal to this. Probability of A and B here is 0.4 probability of B. Okay, so putting the like terms together, you see this is kind of like 1 probability of B, and this is 0.4 probability of B. So we're going to put the things with probability of B on one side. So I'm going to leave this one here, probability of B, and I'm going to take this one over. So if this comes over, it's going to become minus 0.4 probability of B. Then if this comes over, it's going to become positive 0.48. So it's equal to positive 0.48. Okay, these numbers are very cramped up. Let me just move this down. Okay, so what is the probability of B minus 0.4 probability of B? Remember, in front of this probability of B, there's basically an invisible one. Okay, so it's like these are two like terms. So saying 1 minus 0.4, and that gives us a 0.6. So it means we have 0.6 probability of B being equal to the 0.48. So to solve for the probability of B, we're just going to now divide both sides of the equation by 0.6. And let's see what we get. So finally, the probability of B would be equal to, so 0.48 divided by 0.6, and that is 0.8. So it's equal to 0.8. Okay, so that was for 3 marks. That was an interesting question. I've not really seen them do something like that before. Okay, moving on to the next question. Okay, and now we are on the last question for this paper. The question says, okay, let me use yellow. The question says there are 120 passengers on board an airplane. So they probably meant on board on an airplane. Okay, so passengers have a choice between a meat sandwich, or a cheese sandwich. Okay. But more passengers will choose a meat sandwich. Okay, I don't really, you look at that kind of information, you're like, why are they telling us this? But more passengers will use a meat sandwich. But okay, let's keep that information. Then they say there are only 120 sandwiches available to choose from. So only 120 sandwiches. Okay, cool. 120 sandwiches are available. And then they say that the probability that the first passenger chooses a meat sandwich and the second passenger chooses a cheese sandwich is this. So here's a calculation that's already been made. We have to calculate the probability that, so we have to find the probability that the first passenger will choose a cheese sandwich. Okay, choices. So the minute they're already saying the first passenger will choose this and the second passenger will choose that, 2 selections are being made, or more than 1 selections are being made, you know that this is a tree diagram. So we're going to have this tree diagram, and you see that in the tree diagram, they're only mentioning 2 options, meat sandwich and a cheese sandwich. So here we go. We're looking at it like this. We have meat. I'm just going to call that meat. And this one, cheese. Okay. What they tell us is that they are a total of 120 sandwiches. They don't really tell us how much meat sandwiches there are and the cheese. So what I'm going to do is let's just let the meat sandwiches, let's call that X. And the cheese sandwich, let's call that Y. Okay, so no matter the amount of meat sandwiches we have, since that is X over the total amount of sandwiches that we have. So see this as the selections. People are going to choose a sandwich. There are meat sandwiches and then cheese ones. the first time somebody comes and chooses a sandwich, so the person comes to pick a sandwich, the probability that they will pick meat would be X over 120 because there are only 120 sandwiches. The probability that they would choose cheese would be the Y over 120. Okay, now I'm going to extend to a second pick as well because they said something about the first passenger picking and then a second passenger picking. Okay, so since we have two selections being made, I'm going to make another row. So this is just the total probabilities when the first person comes to make a pick. So after the first person has picked a sandwich, we're looking at it like this. The second person that comes to pick a sandwich, given that the first person picked a meat sandwich, okay, we're also going to have to look at what is the probability that the second person chooses meat or the probability that they choose a cheese sandwich. So if one person, the first person has already picked a meat sandwich, then there wouldn't be 120 sandwiches anymore. This would be out of a total of 119 because one sandwich has been picked already. Now, I'm looking at the fact that I'm saying if the first person picked a meat sandwich, how much meat sandwiches would be left? Since there was X amount of meat sandwiches, it would be one less now. So this, we would have X minus 1. That will be the amount of meat sandwiches we have. And then to find the cheese one, we're saying that given that the first person chose a meat sandwich, what is the probability that the second person is going to take cheese? Well, cheese has not been picked. So there will still be Y amount of cheese. It's still Y. But out of, since meat has been picked, it wouldn't be 120. It would be 119. Okay, then looking at if the first person chose cheese instead. So what is the probability that they're going to choose a meat sandwich? The second person, what is the probability that that person will choose a meat sandwich? Well, cheese has been picked, not meat. So there will still be the total amount of meat sandwiches left, which was X. So that would be X over. But we have to take into account that a cheese sandwich has been picked out. So not 120, but 119 sandwiches left. Then lastly, we're looking at the probability that the second person chooses a cheese sandwich given that the first person chose a cheese sandwich. If the first person chose a cheese sandwich, the total cheese sandwiches were Y. Now it would be Y minus 1 because one less of it would be there since cheese is picked. And then out of a total of 119 since one sandwich is picked. So this is kind of what our tree diagram looks like. But then they gave us some extra information. They told us that the probability that the first passenger chooses a meat sandwich and the second passenger chooses a cheese sandwich. So first passenger chose meat. Second passenger chose cheese. What we're looking at is this probability and that. And we're basically looking at the probability of meat and cheese. And they gave us that probability already. They told us that that is 18 over 85. So if that is 18 over 85, we can go ahead and let's calculate this further. Because when we're speaking about the probability of meat and cheese, what you're really going to do is you're taking the probability of meat, whatever that number is. So that X over 120. And because they say and, you're going to multiply that by the probability of cheese, okay, given that meat was taken, which is Y over 119. And we'll say that that is equal to 18 over 85. Okay. So this is an equation. As you can see, it's an equation with two variables, X and Y. There's something that throughout maths from grade 8 all the way to grade 12, you're going to start noticing this same pattern. If you have an equation and two things are missing, kind of think about simultaneous equations. You need to have two equations at least to be able to solve for those two things. It's kind of like if two variables are missing, they need to give you two pieces of information to be able to actually find those two variables. So this is definitely a situation where we're going to have a simultaneous equation. But right now, this is the only equation that we have, but X and Y are missing. So it means that we have to look in the information above and check there's probably another piece of information we can use in this equation so that we can find X and Y. Okay, so we can just simplify this so long. So this is a fraction being multiplied. When fractions are being multiplied, you just say the numerator times the numerator, which would just be xy. So xy over 120 times 119. 120 times 119 is 14,280. And this is equal to 18 over 85. Okay, so we're just trying to solve or make at least xy the subject. So we need to get rid of this denominator. The only way to get rid of that is to multiply both sides by this number so that that denominator would cancel. So 14,280 multiplied by 14,280. And now this would cancel with this because really this is a fraction, it's like over 1. And you can cancel diagonally when we are multiplying. So we'll just be left with xy here is equal to, and let's find out what this gives us. So this number being multiplied by, so it's really just, let me actually just put it as a whole, 18 over 85 multiplied by 14,280. That gives us 3,024. So you see, two things are still missing. We can go ahead and make one thing a subject. I can go ahead and make x the subject so we can divide both sides by y. And it's okay, we can divide both sides by y. Y is definitely not going to be 0. X and y represent the amount of meat and cheese sandwiches. And it's definitely not 0 meat sandwiches or cheese sandwiches. So this is fine. X is equal to 3,024 over y. Okay, this is the equation we have for x. You see, two things are missing. So it means that there must be another piece of information that we can use to form another equation. Okay, so what other information included x and y? Well, x stands for the meat sandwiches and that stands for the cheese sandwiches. They said, so if we look here, they said that there are only 120 sandwiches available. Okay, so we know that if this is the meat and that is the cheese, if you add them together, it should be equal to 120. So, because that's the total amount of sandwiches we have. That's another equation we can form. X plus y is equal to 120. Okay, there we have another equation. I'm going to call this one equation 1 because it's a linear equation. So do you see now that this is a simultaneous equation? We have a linear equation and we have this type of equation and we need to solve for x and y. Okay, so because y is here on the denominator, I'm just going to make y the subject here so I can just slot it into here. So if I want to make y the subject, I need to get rid of x by taking it over since we are adding here. So this is now y is equal to 120 minus x. And I'm going to go ahead and call this my equation 1 and this one my equation 2. So in order to now solve for one of it, we're going to go ahead and substitute equation 1 into equation 2. Okay, so when we do that, we're going to say, we're saying x is equal to 3,024 over y. And our y is now this 120 minus x, so 120 minus x. Okay, so this is the equation. We're going to solve for x here. Okay, to solve for x in this equation, let's look at the fact that we can put this over 1. And then we have an equal to sign. So it's a fraction, and we can cross multiply. So let's cross multiply. X multiplied by 120 minus x. It's really just like saying x times 120 minus x. The x needs to multiply to the 120 and the x as well. Is equal to, and then we're going to say the 1 multiplied by 3,040, which stays 3,024, sorry. Okay, so we have this, and let's multiply this x in here. So that will give us 120x minus x squared is equal to 3,024. Then, because the x is negative here, let's just go ahead and take it over instead and take everything over because this is going to be a trinomial. So we have 0 is equal to x squared, and then we have minus 120x because I'm taking that 120 over. But then this is already on the right hand side, so it's just a positive 3,024. Okay, so here we have a trinomial. We have to factorize this. 0 is equal to, open up 2 brackets, and we have x and x. Now the middle is negative, meaning both of them should be negative. So let's think about factors of 3024 that can give us 120. You can use the quadratic formula, but most of the time in these questions, there's usually like a mark for the factors. I'm not sure about this one though, but I'm still going to try and find those factors. Let me just check which ones work. Okay, so I tried a bunch of numbers, and when I try 3024 divided by 36, it gives me 84. But if I say negative 36, because they're going to be negative, minus 84, also negative, that gives me negative 120. And so see, I get the middle term. Okay, so I'm going to use that negative 36 and minus 84. Those are our numbers that we have. Okay, so we can go ahead and say it now. Finally, x is either equal to 36 or x is equal to 84. Okay, we have two answers. Okay, but let's see where this goes. This is our answers for x. And now we can solve for y by substituting our x values into this equation, into equation 1. So if you like, you can call this equation 3. And you can just say we're going to substitute equation 3 into equation 1, because equation 1 was the one with y perfectly sitting like that. So y is equal to 120 minus x. Y equals 120 minus the first x value, we have 36. So minus 36. And y is equal to 120 minus 36. That is 84. Okay. Or if you say y is equal to 120 minus 84, so of course then that will give you 36, because if 120 minus 36 is 84, then 120 minus 84 is 36. Okay, so this is what we have. It's either that x is equal to 36 and y is equal to 84, or x is equal to 84 and y is equal to 36. And I think this is where that piece of information that looked very unnecessary comes in. So remember that they said this. They said, but more passengers will choose a meat sandwich. I think that was their hint to tell you which one to choose. More passengers will choose a meat sandwich. So if more passengers are choosing meat, remember meat was x. So it just means that x, the meat sandwiches, need to be more than cheese. So we're going to take the one that has more of the meat. Here we have 36 as the meat sandwiches. Here we have 84. So it means that we need to take this option. Okay, so it just means x is equal to 84, y is equal to 36. And now let's go ahead and find out what they were asking for, because now we know the meat and the amount of cheese that they are. So we can actually just find what they were asking for. They want us to find, this is a very long question for 5 marks. Okay, but they want us to calculate the probability that the first passenger will choose a cheese sandwich. Okay, yeah, that's another headache on its own. Okay, so the first passenger will choose cheese. So it doesn't matter what the second passenger chooses, basically. They just want the first person to choose cheese. So this is what we're going to be looking at. Let me actually get rid of these highlights. We're looking for the first person just needs to choose cheese. So you need to take this. You need to take cheese. First person takes cheese. The second person takes meat. Or it could be a situation where the first person takes cheese and then the second person takes cheese. You see, they're not being strict on, they're not telling you anything about what the second person chooses. They just want the first person to choose a cheese sandwich. As long as the first person chooses it, you need to take those probabilities. So, in other words, we are taking the probability of cheese and meat, or we have to also have to consider the probability of cheese and cheese. So it's really, you're considering the fact that the first person may take cheese and then the second person takes meat. Or it could be a case where the first person takes cheese and the second person takes cheese. You see, they just want the first person to take cheese. So as long as the first person is cheese, we need to take that. Okay, so this is really what we are looking for. That's really what it seems like they're asking for. So I'm going to take this and let's go ahead and calculate what this is going to be. Since I'm saying or. Now, when you see the word or actually means to add. And you can really see that like this. For example, if you had a coin and someone asked you, what is the probability that you're going to land on heads? You would just say, oh, that's 1 out of 2, because it's one head out of the 2 faces that they are on this coin. Okay, but if you were asked what is the probability that you're going to land on heads or tails, then that would be 100% chance. There's only two faces. You either land on heads or you land on tails. So that's 100% chance, which is really 2 out of 2, which comes because we say the 1/2 from the probability of heads and the 1/2 from the probability of tails, and we add them together. Okay, so when you say or, it increases the chance and it means to add. So this is what we're going to do. We're going to take the probability of cheese and meat. Okay, and cheese and meat would be this. So cheese and meat. Now that we know what these numbers are, we can fill them in. So cheese and meat, taking this and this. So y over 120 times x over 119. That's what we're going to take here. And we're saying, because we have or, we are going to add that to the probability of taking cheese and cheese. And that was the y over 120 and the y minus 1 over 119. Okay, and now we can just fill in what x and y are in this. So y is 36, so that's really just 36 over 120 being multiplied by x is 84, so 84 over 119 plus here y is 36, so 36 over 120 multiplied by y minus 1. 36 minus 1 is 35 over 119. So let's put this onto the calculator and this will give us our answer. And we get 3 over 10 as our final answer. So the probability that the person will take cheese first, and I even use the number first, is equal to 3 out of 10. And then we have 10.1 saying, in a survey, 1,530 people were asked whether they had ever broken a limb. The results of the survey were as follows. So we have the people who have broken a limb and people who have not broken a limb, and as well as their genders as well. And in 10.1.1, we're told to calculate the values of A, B, C, and D. Okay, so with contingency tables, what you should know about them is how they add up. So you see the broken a limb, if we take this 463 and we add it to A, we will get this number. And if we take this, add it to this, we will get this number. So they add up like this, like that. And also, if you take this 463 people and you add it to B, that would give you that total. And if you take A and C, it will give you the total of D. Likewise, also, if you take this people and you take that people, it will add up to the total number of people. Okay, so that's how it adds up. So we can start in alphabetical order because that would just be easier. So A, to find A, we're going to say the 463 people plus A, that will give us that. So it means that A would be equal to 913 minus 463 people. And A gives us a total of 450 people. So now we have A, you can fill that in as you get it. So A is equal to 450 people. We can go ahead and find B. So B, to find B, if you take this 463 and you add it to B, you will get that. So that means B would be equal to this total, 782, minus this 463 to get B, minus 463. And let's see what that gives us. And B is equal to 319. So we have B as 319. It's always good to fill it in as you're going on. Then let's find C. So C, we can find C by saying 319 plus C is equal to this. So C would be equal to the 617 people minus the 319 people. Okay, so let's see what this gives us. So C is equal to 298. Okay, so fill in C, 298, and then we can go for D. So lastly, D. To find D, since this plus this is equal to D, we can just find it like that. You could have also said this 1,530 minus the 782, you would still get D. So I'm just going to say D is equal to the 450 people plus the 298 people in order to get D. So D is equal to 748 people. Okay, so that's A, B, C, and D for 4 marks. Then Then moving on to the next question. So the next question, 10.1.2 says, if a person is chosen at random, what is the probability that it will be a female who has not broken a limb? So the person is chosen from the group, entire group of people at random, and she has to be a female who has not broken a limb. Okay, so let's go to the females who have not broken a limb. So female who has not broken a limb. It would be this 298 out of the total people. And the total people that they are would be this. That will tell you the total. So it's 298 over 1,530. Okay, and you can also simplify it further. So if you do simplify it further, it will be 149 over 765 because they just want the probability. So if you put this also as a percentage, it will also be fine. Okay, then moving on to the next question, 10.2. So 10.2 says, 2 learners are selected at random from a group of 10 boys and 12 girls. Determine the probability that 10.2.1, they are both girls. Okay, so the fact that they're saying that 2 learners are being picked at random from a group, I want you to see it like this. It's not a case that the 2 learners are being picked at once. They're being picked one after the other. And that's usually what they mean when they say 2 learners are picked or 2 apples are picked. This refers to a tree diagram. Okay, so this is how we're going to draw the tree diagram. Because we have boys and girls, we're going to have 2 branches. So we're just looking at the first pick, what is the chance that you're going to pick a boy? Now, nobody has been picked yet. So that means there are still 10 boys out of a total of 10 plus 12, 22 learners. So the first time you try to pick, the chance of picking a boy is 10 out of 22. Then the chance of picking a girl, because nobody has been picked yet, there's still 12 girls. So it's 12 out of 22. So this will represent the probability of the first pick. This is you pick out and you could either pick out a boy or you could pick out a girl. This will be the probability of picking a boy and that will be probability of picking a girl. Now, what I do find weird is that they don't mention that these learners are not being put back in the group again. They're just saying that 2 learners are selected at random. They're not saying that and the learners are not put back in the group. But I assume from the way this is and the questions they're asking, they probably mean that 1 learner is picked out and then the learner is not told to stand back again in the group. So that 1 learner is already out of the group. Okay, so in that case, the events here, okay, the probabilities of these ones would affect the next pick. So we would look at it like this. It would be a case of, okay, let's say in the first pick, because this represents the probabilities of the first pick. So if in the first pick they picked a boy, what is the probability of picking a boy again? Since they have picked 1 boy already, there wouldn't be 10 boys anymore. There would be 9 boys. And now, because there were 22 kids, they're not going to be 22 learners anymore. They're going to be 21 learners because 1 has been picked. So out of 21. And then the probability, so that will be boy. Then if they picked a boy, so given that a boy was picked, what is the probability that they will pick a girl in the second pick? Because this part represents the second pick. Because a girl has not been picked, we're saying given that a boy has been picked. Then what is the probability of picking a girl? Well, we still have 12 girls because no girl has been picked yet. So 12 girls, but out of not 22, but 21 learners because 1 boy has been picked already. Okay. Then in the same second pick, we're saying, okay, what if it was not a boy that was picked in the first pick? Let's say it was a girl that was picked in the first pick. So what is the probability of picking out a boy now? The probability of picking out a boy, if a girl was picked at the first pick, there would still be total of 10 boys. So 10 out of but 21 learners, because we're saying given that a girl was picked, so they're not 22 learners anymore. And then to look at this last branch, which we'll be speaking about, the probability of picking a girl, we would say since a girl has been picked, now what is the probability of picking another girl? A girl has been picked, there wouldn't be 12 girls anymore. There would be 11 girls out of a total of 21 learners. So that's how we draw the tree diagram. Okay, now that the tree diagram has been drawn, we can now answer their questions. The first question, 10.2.1 says, we need to determine the probability that they are both girls. So what they mean by in 10.2.1, both girls, we're just looking for the probability of in the first pick, you pick the girl. And then in the second pick, you also pick the girl. That's what they're looking for. They're looking for the probability of girl and girl. So we're looking at it like this. In the first pick, a girl was picked. And the probability of that is 12 out of 22. Then in the second pick, a girl was also picked again. And the probability of that is 11 out of 22. And when we move across like this, we multiply. So we're saying 12 out of 22 multiplied by 11 out of 21. And let's see what that gives us. And this is equal to 2 over 7. And I'm just going to leave it as a fraction. Okay, so that is 10.2.1. Then in 10.2.2, we need to determine the probability that 1 is a boy and 1 is a girl. So with this one, this is how we need to think about it. Remember, there is a first and a second pick. All they are saying is they want the probability that 1 will be a boy and the 1 will be a girl in any order. They didn't specify that the first must be a boy and the second must be a girl. Or they didn't even say the first must be a girl and the second must be a boy. So we need to take them in any order. So really what we're going to take is we're taking the probability of a boy and then a girl, or we could also take the probability of a girl and then a boy, as long as one of them is a girl and one of them is a boy. So you see, we have to consider these two cases. And when you see the word or means to add. And a simple explanation for this or would be, let's say we had a coin and I asked, what is the probability of flipping this coin and landing on heads? So that would just be 1 out of 2. But what if I said, what is the probability of flipping this coin and then landing on heads or tails? Well, the thing is that there's only 2 outcomes here. It's either you get heads or you get tails. So what is the probability of landing on heads or tails? You will always land on either heads or tails. So that would be a half for the heads plus a half for the tails. And in total, it's really just 2 over 2, which is 100% chance. There's 100% chance of landing on heads or tails, because when you say or, it increases the chance. You can land on either one. Okay, so let's go ahead and look for these on here. So we're looking for the probability of a boy and girl first. So we're looking for the probability of boy in the first pick and then a girl in the second pick. So this is what's going on here. Probability of picking a boy the first time will be 10 out of 22. And then we have to say multiply because we have and. Multiply by the probability of picking a girl in the second pick, which is 12 out of 21. So 12 out of 21. Then we have or. So we're adding that to the probability of the second one. So we have now the probability of picking a girl first. So picking a girl in the first pick. And then a boy in the second pick. And then a boy in the second pick. Okay, so picking a girl first, that will be the 12 out of 22. Multiplied by picking a boy would be 10 out of 21. Okay, then we'll just multiply this and add, put a plus in the middle, and let's see what we get. And all of that on the calculator is equal to 40 over 77. And I'm going to just leave it as a fraction. So 40 over 77. That is the probability of picking either a boy and girl or a girl and boy, which is 1 is a boy and 1 is a girl. So you have to consider that they can be picked like that in any order. Okay, so now we move on to the next question, which is on a Venn diagram, 10.3. So 10.3 says, in the Venn diagram below, M and N are independent events. Okay, that is an important thing to consider. Then we have calculate giving answers correct to 2 decimal places. So 10.3.1, we have to find the value of x. Okay, so looking at this Venn diagram, first of all, so just understand that x, whatever this decimal is, that would be the probability of event M only. So this is the part of M that doesn't include N. Then this in the middle is the intersection of M and N. And then 0.45 is the probability of event N only. Then we have Y, which is neither M or N. So to find the value of x, What would include X? Well, we have to take what they said in the beginning. They said M and N are independent events. And this is the rule for independent events. So if events are independent, then this is what it means. And I'm just going to relate it to this though. Then it means that the probability of M and N would be equal to the probability of M multiplied by the probability of N. That's the rule for independent events. So we're going to use this. The probability of M and N, that is just the intersection of M and N, which is 0.12. So that is 0.12 is equal to the probability of M. Remember, this one is just the probability of M only. The entire probability of M is the whole circle of M. And you see that would include the X plus the 0.12. And that's what we have to do. Probability of M would be the X plus the 0.12 multiplied by the probability of N. That will also be referring to the entire circle of N. So that would be the 0.12 plus the 0.45. So let's see what that is. 0.12 plus 0.45. And as a decimal, we get 0.57. So multiply by 0.57. And now you can see we have an equation where we need to solve for X. So to solve for X, notice that this is being multiplied to these that have two terms in it. So it's really supposed to multiply in. So if I just have to rewrite it, it looks like this. It's 0.57 being multiplied by X plus 0.12. And then we have a 0.12 here, of course. Then we have to get into the X. In order to get into the X, we can just get rid of the 0.57 by dividing both sides of the equation by 0.57. And let's see what we get. 0.12 divided by 0.57, that gives us, now I shouldn't take a rounded off answer because we have not solved for X yet. So I'm going to leave it as a fraction. So I'm going to take 4 over 19. That is equal to, that cancels. And now we have X plus 0.12. Then if you take the 0.12 over by just saying that 4 over 19 minus the 0.12, that will give you an answer of X. So let's see what X is equal to. This minus the 0.12. And now I can leave that as a decimal. The final answer can be rounded off to 2 decimal places. That's what they said. Correct to 2 decimal places. So here, that is just going to be a 0.09. And you see it's not going to round up. So 0.09. That's our answer for X. Okay, so that is 10.3.1. Then we move on to 10.3.2. Okay, so 10.3.2, the value of Y. So we have X, we can put that in. That is the 0.09. The value of Y is something you need to know about Venn diagrams. If you take every number, okay, as it is as a decimal in the Venn diagram and you add everything up together, it must give you 1. Because remember, when these things are as decimals, it's the same as them being in as a fraction. So these are really just the probabilities of each event. This 0.09, that is the probability of event M occurring. Okay, so that is really 9%, and this is 12%, and this is 45%. So if we add everything up together, it should give us 100%. So as a decimal, that is just the number 1. So we can take everything added up and it should give us 1. So that's 0.09, 0.12, 0.45 plus y as well should be equal to 1. So that's the equation we're going to have. So since all of these are numbers, I'm just going to add them up first. And when I add all of these decimals, I get 0.66, and we say plus y is equal to 1. And so y is equal to 1, and we're taking the 66 over minus 0.66, and y is finally equal to 0.34. And that's our value for y. And now we are finally on question 11, the last question for this paper. We have 11.1 saying events A and B are mutually exclusive. It is given that probability of B is 2 times the probability of A. And then the probability of A or B is 0.57, and we have to calculate the probability of B. So use what they told you. They told you that probability of A and B are mutually exclusive. When events are mutually exclusive, this is a diagram of mutually exclusive events. So a way that I help my students to remember this is we look at mutually exclusive like this. So we're looking at event A and B. If events are mutually exclusive, then it means that these events have mutually agreed to exclude each other. So you can see there is no intersection in this case. So because there's no intersection, that's the whole point of mutually exclusive events. Mutually exclusive events, the probability of A and the probability of B would be equal to 0. We don't have an intersection. And that's a big part of this. So they also tell us, look at the other information they tell us. Apart from telling us the probability of B is 2 probability of A, they also tell us about the probability of A or B. So when we are putting these probabilities together, so let's see how we would add them. We know that the probability of A or B is going to be equal to the probability of A plus the probability of B minus the intersection, right? But in this case, we know the intersection is 0. So you don't even have to include that. We can just remove that. So you can't say minus 0 and show them that, or you could even remove it. It's fine. They would know that, okay, this is mutually exclusive events. So now we know the probability of A or B, that is 0.57. So 0.57 is equal to the probability of A. They don't tell us anything about that. They only tell us what the probability of B is, but they put it in terms of the probability of A. So we can just say probability of A, leave it like that, then plus the probability of B. That is 2 times the probability of A. So we're saying plus 2 times the probability of A. So you can see that this is a case where they are making the probability of A the variable that you have to find. Okay. So that is like saying 1 probability of A plus 2 probability of A. That will be equal to 3 times the probability of A. And that's 0.57 that we have. Then we just have to solve for the probability of A by dividing both sides of the equation by 3. And so 0.757 divided by 3 would give you that. So I'm just going to put it in decimal form. It means therefore that the probability of A is equal to 0.19. Okay, so that's the probability of A. But let's also just not forget what they specifically asked for. They specifically asked for calculate the probability of B. So now we know what the probability of A is. We can find the probability of B because they told us the probability of B is 2 times the probability of A. So just say probability of B is equal to 2 times probability of A. We know what that is. That is now 0.19. Okay, so we're just substituting that in that place, in probability of A's place. So that will finally give us, so just say 0.38. So that is the final answer that they are asking for. Okay, so 11.2 says, a box of 40 calculators is sent to a store by a supplier. The owner of the store is not aware that 5 of the calculators are defective. Okay, so then 2 calculators are selected at random from the box, the first one not being replaced before the second one is selected. So 11.2.1, they say, what is the probability that the first calculator chosen is not defective? Okay, so the way this information is being put, this is clearly a tree diagram that we're going to need to draw, because you can see that there's 2 selections going on. First time a calculator is selected, then the second time a calculator is selected. But in this case, remember they say that it is not replaced after the first one is selected. So in total, there are 40 calculators. Then we know that 5 of the calculators are defective. So let's put down a tree diagram. We're going to have calculators and there'll be ones that would be defective. I'll just call it defective. And the ones that are not defective, defective. So there are a total of 40 calculators. I need to move this down because it's not going to be space for the other part. Okay. So we know now the amount of calculators that are defective. They told us 5 of the calculators are defective. So there are 5 calculators that are defective out of a total of 40 calculators that we have. And then the calculators that are not defective would be minus 5 of that. So it's going to be 35 out of 40 calculators that would not be defective. Okay, so this one would represent the probability of the first pick. The first time somebody reaches in and picks out a calculator, they can either get a defective calculator or a not defective. The first time when nothing has been picked yet, the chance of picking a defective calculator would be 5 out of 40. The chance of picking not defective would be 35 out of 40. Then in the second pick, now this is where we look at that. If they picked a defective calculator, what happens? So again, we're going to look at the probability of defective calculators and not defective calculators. If they picked out a defective calculator, then it would mean that there's now one less defective calculator, meaning there is 4. The chances of them picking out a defective calculator would be 4 out of not 40 calculators anymore, but 39 calculators in total. So this would be the chance of picking out a defective calculator. Then, again, if they chose a defective calculator, what is the probability that they would pick out a not defective calculator? The not defective ones were not touched. Only the defective one was touched the first time, was picked out. So it means that there are still 35 not defective calculators, but out of a total of 39 because one defective calculator has been picked out. Then we'll also look at the second part. Again, we're looking at the defective calculators and the non-defective calculators. So if you picked out a non-defective calculator, what is the chance that you're going to pick out a defective calculator the second time you pick? So we would have to look at it like this. The non-defective one has been picked, meaning the defective ones are not being affected. Okay, so remember this part, okay, represents the second pick. So we're just saying if the first pick was actually a non-defective calculator instead, then it means that the defective calculators that would still be there would still be the total of 5. Because this time we didn't pick out a defective. So it's still 5 defective calculators, but a calculator has been picked out already. It's a non-defective one. So there's still 39 now calculators left. Then the last one, what is the probability that we're going to get a non-defective calculator if you picked a non-defective calculator the first time? So there'll be one less of it. So instead of 35, there's now going to be 34 non-defective calculators out of a total of 39 calculators. Okay, so that's what the tree diagram looks like. So let's just look at what exactly they are asking for. They said, what is the probability that the first calculator chosen, so probability that the first calculator chosen is not defective? The position matters a lot. They're saying in this one, the first calculator chosen needs to be not defective. They are not bothered about what the second calculator chosen is going to be. So when we're looking at this is what they're saying. The first calculator just has to be not defective. So if we're looking at the first pick and the second pick, first calculator and second calculator that's been picked, we just want this one to be not defective. The second one can be anything. So the second one can either be defective or it could be the case of it was not defective. As long as the first one chosen is not defective. So these are the two cases you need to look at. It's not just one case. So it doesn't matter what the second one is. So this is what we're going to be looking at. These two, we're going to be looking at a case of when in the first try, we pick a non-defective calculator, and then in the second one, multiply by the second try a defective calculator. So from that, you see now that what we have is probability of the first one being not defective would be, we would first have the not defective, which was this, the 35 over 40, multiplied by this 5 over 39. So that's the first case we could have. Or we could have the case of this. And remember, when you say or, It's really to add. Because if I say, what is the probability of getting heads or tails, then it means I can get either heads or tails. It's still fine. So you have to include the probability of heads and also the probability of tails. So we need to add. So we're saying plus what this one will give us. So we're looking at, first of all, we need to pick a not defective calculator in this first pick. And then in the second pick, we should also pick a not defective calculator. So you need to first define these things and see what are all the things they're talking about first. What are all the situations they are talking about first? So we're adding that to this being not defective, which is 35 over 40, multiplied by your not defective here, which is 34 over 39. Okay, so you can put these in brackets if you want. And then let's see what that gives us. And when we put that all in, it actually just gives you 7 over 8 as your answer. So you can put this number as a decimal. You can also put it as a percentage, but it's also fine like this. Okay, so that is the answer of the first one. Okay, then the next question, 11.2.2, they say, what is the probability that if two calculators are selected? Okay, of two calculators, of course, will be selected. But then, okay, they're saying one calculator is defective and the other is not. Okay, so let's think about what all of this would mean. One calculator has to be defective and the other has to be not. So no matter how they are being picked, you just need to make sure you have one defective and one not defective. Look at all the things we need to include now in this. So let me erase all of this first. So we're still looking at the first and the second picks, or the first and second calculators that have been selected. Is defective, one is not. It can be in any order. They didn't specify. If they said the first must be defective and the second must be not, then you're going to have to take defective first, then not defective second. And then that would be all. Okay, you just multiply them like that. But they just said one calculator has to be defective, the other must not be defective. So we can take this in any order. So we have to take both situations. We have to take what the first one is defective and the second one is not defective. Or it could be the situation of the first one being not defective and the second one being defective. So you have to take these both cases because they were not specific. This would be before under this criteria where one calculator is defective and the other is not. Okay, so let's just find those, and then because we have all, we add them together. So we're looking for defective first. So defective 5 over 40, and we're going to times that by, so that was the defective one, 5 over 40, and then multiplied by the not defective in the second pick. And not defective in the second pick would be this one. So that would be the 35 over 39. So multiply by 35 over 39. Then that probability, we're also going to add it to the second case. So that was just the first case. Okay, and then the second case, so after this, the second case is we have to take a not defective, and that would be the 35 over 40 multiplied by a defective one in the second pick. So in the second pick, we have to take a defective. That will be 5 over 39. So that's what that looks like. Okay, so we can just go ahead and simplify that and see what we get. Okay, and the answer we get is, as a fraction, is 35 over 156. So you can put this as a decimal if you want. You can also put it as a percentage. It would be accepted. Okay, so that is 11.2.2. And then we have 11.2.3, and this says, what is the probability that if two calculators are selected, both are defective? Okay, so two calculators, of course, are going to be selected, but now this time, both need to be defective. So we're actually just looking for here the probability of defective and defective. That's what we're looking for. So that is only one case. It's not two things that we have to consider. It can only happen once. So defective and defective will happen over here. The first one is defective, and the second one, the second pick, is also defective. So those two, just multiplying those two together, and we'll work with that instead. So that's the 5 over 40 times 4 over 39. And as a fraction, I just get 1 over 78. Okay, so that's the answer for that one. And now we move on to 11.3. So 11.3 says 4 different economics books and 3 different life sciences books are required to be placed on a shelf. Okay, so 11.3.1, if you decide to place any book in any position, in how many different ways can you arrange the books on the shelf? So we are not grouping the books, we're just putting them in any way. Remember, you basically have to just see how many books do we have. We have economics book, so 4 books are economics books, 3 books are life science. So in this case, we're not grouping them or anything. We just have to find out how many books are there. There will be 7 books in total. So to find out how many ways we can put them on the shelf, you can see it like this. The first book will have 7 places that it's allowed to sit in, because it can either sit in the first position, second, third, all the way to 7. So that's 7. Then multiply by, once the first book has been placed, wherever it's been placed, the second book has 6 more positions to be placed because the first book has already been placed down. So the second book has 6 available spots to sit in. So that's times 6. Third book has 5 available spots. The fourth book, 4 available spots. The third book, 3 available spots. Then 2 available spots and 1. So that is really just 7 factorial, which will give you, which will be equal to 5,040. So these are 5,040 ways that you can arrange these books on the shelf. Okay, so that is the first one. Then the second one says, if 2 particular books must be placed next to each other, in how many different ways can you arrange the books on the shelf? Okay, so now there's a grouping happening here. They don't tell us which 2 specific books, but we know that 2 books are going to be grouped together. So I'm going to put it like this. This is 2 books being grouped together. Remember, we have 7 books in total. So the other 5 books are just going to be put here. So there's your other 5 books just being put there as well. Okay, so since now we have to just find out how many different ways they can be arranged. This is how we look at this. First of all, you're going to take these 2 books and you're trying to see how many ways can they be put as they are as a group, because they need to be next to each other. So here's your first book, here's your second book. You can either put it in this arrangement where the first one is first and the second one is second. So that's 1. And then you can also put it where the second one is first and the first one is second. So there's 2 total ways that these 2 books can be arranged where they currently are. So that's 2 factorial. That's what we just call that. Now let's look at the other books. The other books, we can pretend that they're being grouped, but not together, alone. Like this one book is a group on its own. That one is a group on its own. That's alone, and that's alone. There's a reason I'm calling them just groups for a reason. Okay, so if you look at each of it, it's really just how many ways can this one group sitting here be arranged? Just 1 factorial. Then multiply by how many ways can this one group be sitting on its own? Just 1 factorial. And this is what I'm going to do here. So multiply by 1 factorial for each book. And then, because all the books need to be allowed to move around everywhere, they cannot just sit like this. For example, this book can be sitting here instead. And this book can be sitting here instead, or even here. They should still be able to move around. This is what we can do. We're looking at it as if they were groups. And now we just have to count how many groups have been formed by this. It's really this being your first group, that's your second group, third, fourth, fifth, and sixth. So now there are 6 groups being formed, and you need these books to be able to move around anywhere as well. So we'd multiply that by 6 factorial, so that your groups are allowed to move around. So it's kind of like your books are now allowed to move around. Putting this together was so that these 2 stay together and they are allowed to move around, as in first book and the second book, or it could be a case of the second book and the first book. But when we say times 6 factorial, we're basically giving all of these books the right to be placed anywhere. So this as a group can now even sit in between these 2 groups, or in between those 2 groups, or even all the way at the end. So that's why we multiply by 6 factorial. We kind of look at each of these as if they were individual books. But then we have to say 2 factorial here, because these 2 books don't always have to sit as 1 and 2. They can sit as 2 and 1. Okay, so if you look at this and you just simplify this, what this actually says is 2 factorial, and then if you multiply all of these 1 factorials, they're just going to give you 1 no matter what. So it's really 2 factorial multiplied by 6 factorial. And that will give you 1,440 ways. Okay, and then we are on to the last question. And then the last question, 11.3.3 says, if all the economics books must be placed next to one another and all the life sciences books must be placed next to one another, in how many different ways can you arrange the books on the shelf? So again, this is a case of grouping the books. We're placing them next to each other. If you use the same principle in the previous question, this will work out. So think about it like this. We're looking at the economics books. So eco, we have 4 economics books over here. Then we have life science. So LS, we have life science. Let me just put that in blue. So 3 life science textbooks over here. And what we're going to do is we're creating a group. We're creating a group for economics and for life science. So this is one group. This is another group. And what we're going to do is, for this to be able to move around in any way, we're looking into the first group. We have 1, 2, 3, 4 books in there. These 4 books should be allowed to sit in any arrangement. It doesn't have to sit as 1, 2, 3, 4. It can be 2, 1, 3, 4. And all the other ways. Now, the total ways that these books in the economics section can be seated or can be placed on the shelf, that would be the 4 factorial. That's just for this one group here. Then for the life science, for this group, the way these books can be seated, it's like you still have the first book, second book, and the third book here. There are 3 books, so we can say multiply by. They should also be allowed to sit in any way as they are inside this group. So that is going to be multiplied by 3 factorial. Okay, because it can be the first book, the second book, and the third book. Then it can be a case of the second book first, then the first book, and then the third book, and so on. So it will be 3 factorial ways that they can be seated in total. But then, so that the books can all move around freely, as in it doesn't have to be economics seated here, all of them packed together here, and then life science, all of them packed together here. So that doesn't happen, we look at how many groups have been created. We created only 2 groups. It's this, the economics, and the life science. So then we multiply that by 2 factorial, so that we're looking at the group seating like this. These books can either be placed on the shelf as first your group of economics textbooks, then your life science, or it could be put in the case of first the life science, then the economics. That's where the 2 factorial is coming from. Okay, so that will give you your answer. So let's go ahead and see what that gives. And here there are 288 ways that they can be seated. So it's always good to first create the groups that they spoke about. Like here as well, I also created groups. So they only grouped these 2 together, and then the rest were just on their own. But I pretended each book was an individual group. Okay, so that is a method that you can use to calculate this. So that is the last question. The answer is just 288 ways. And that's it for this video. And now we're on question 10. And question 10.1 says, A, B, and C are 3 events. The probabilities of these events, or any combination of them, occurring is given in the Venn diagram below. So we have this Venn diagram, and they've given us the probabilities of each event occurring, and of course combinations of them. Now the first question, 10.1.1, says, if it is given that the probability that at least one of the events will occur is 0.893, calculate the value of A. You need to calculate the value of Y. That is the probability that none of the events will occur. Okay, before even diving into this question, I want to explain something quickly about Venn diagrams. Venn diagrams are one of the simplest parts of probability. When you get a Venn diagram, it's really something that you shouldn't be worried about. And I explain Venn diagrams in more detail in these two videos that I'm showing you now. So you can check out those videos if you know that you struggle with Venn diagrams. Okay, so looking at each of these numbers, first of all, I want you to notice the fact that everything is in decimals. Now, when we're speaking about the probabilities of an event occurring, right? All the events, all the possible outcomes, it is the sum of every single event that could possibly occur. Because these are in decimals, if you had to find the sum of every single event that will possibly occur and you add them up together, it's going to give you 1, which really just means one whole. So this is 0.05 out of that whole, and so on. That's how all these numbers are being represented. Okay, so that first question, A, they want us to find y, which is the probability that none of the events will occur. So this is the one outside. Something I want you to realize, because it is outside and all of these ones are in these circles, remember that every single thing here adds up to 1. So if everything here adds up to 1 and y is just sitting outside, so to find y, we would just say 1 minus the sum of everything, the probability of A or B or C. Okay, now look at the scenario and see, look at the case they gave you here. So they told you that if it is given that the probability that at least one of the events will occur is this number, then you have to calculate the value of y. At least really just means at lowest. So they're saying the probability of at lowest, the minimum amount of events that should occur is 1. So if we look at these circles, let's see which ones would be included in this. Okay, so at least one event will occur, meaning the minimum values, the minimum amount of events that must occur is really just 1. Okay, one event. So as long as it has one event or more, then we're going to take it. So look at this one. How many events does this include? Well, this is the probability of A only, so this is included. This one, how many events is included here? This is the probability of A and C. So there's 2 events, so it's included because the minimum amount of events we must have occurring is 1 event. So as long as it's 1 or more, we take it. Look at that one, C, right? C is only C. This amount here is for only C. So it means that we include that because 1 event is occurring. This one, 2 events are occurring. So the minimum amount is 1. That's also included. This will also be included. 1 event is occurring. This is included. 2 events are occurring. And the middle will definitely be included because 3 events are occurring. The minimum amount of events that we need to occur is 1. So anything that is above 1, we take. Anything that is 1 and above. So we also take that. So now we understand this as this part says at least one of the events will occur. That is the sum of all the probabilities inside all the circles. So all those probabilities, they add up to this number. So in order to find y, again, just like I had previously here, but I removed it, where I said 1 minus the probability of A or B or C, probability of A or B or C is also the sum of every single thing here. That's why we find y by saying 1 minus this number, because this is at least one of the events occurring. That's the sum of all your circles, everything that is in these circles. So 1 minus 0.893, that is going to give you your number. And put that on a calculator and this is what we get. We get 0.107, but you can round off to 2 decimal places, so that will round up. And so that is 0.11, and that is the value of y. Then in B, they ask us, we need to determine the probability that all 3 events will occur. Remember, all 3 events occurring means all 3 events are occurring at the same time. So that is x, of course. They did mention that that is x. So to find x, the information they already gave us above is more than enough to find x. We already found y, that's not a problem. But to find x, since we know that this, right, at least one of the events will occur is this number. And we know that that is the sum of everything we have in the circles. Then we must just add all the numbers in the circles, including x, and make it equal to this, because we know that it sums up to that. Okay, so let's go ahead and do that. So there we go. This is the sum of everything in here. And then we just need to solve for x. So add all your numbers together. So I'm going to add all of this with all of this and then say plus x. Or I'll really just start with x plus and then all the numbers. And when I add up all the numbers that are underlined in blue, I get 0.733. So I'm just going to say x plus 0.733, that is equal to this number that we have, 0.893. Then to solve for x, you're just going to go ahead and take that 0.733 over, so that is 0.893 minus 0.733, and then put that onto the calculator, and that will be your answer. So x is equal to 0.16. Okay, and since I have these numbers down, I'm going to fill them into the diagram, and then just so that we have all those values. Okay, moving on to the next question. The next question, 10.1.2, says, determine the probability that at least 2 of the events will take place. So if you watch my video on Venn diagrams, you'll be able to answer this question very easily. So just break down the question. At least 2 just means that at lowest, the amount of events that should take place is 2 events. So it means that the minimum amount of events we're looking for now is 2. So we're only going to take those values that have a minimum of 2 events. So as long as it is 2 events or more, then we're going to take those. Okay, that's what at least 2 means. So we're going to go up here and let's look. So first of all, 0.05. This is the probability of A occurring only. That only includes 1 event, so we cannot include that. If you also look at C, that is the probability. This number here is the probability of only C occurring, and that is the probability of only B occurring. So we cannot take those because only 1 event is occurring in those numbers. So in these ones though, look at the intersections. How many events are occurring here? That's 2 events. So we're taking that. We're taking 2 or more. Here, that's also 2 events, A and B. And then here, that's B and C, that's 2 events. And finally, the intersection. How many events occur here? 3 intersections, A, B, and C all occur here. So these are the numbers we're going to take. We will add these numbers up and then give them that answer as a decimal as it is. Okay, so that is 0.15 plus 0.1 plus 0.16 plus 0.2. And then we get 0.61. So that is the probability that at least 2 events will take place. Okay, so 10.1.3 says, are events B and C independent? So the rule for independent event is this. If events are independent, then you will notice that, and I'm going to use B and C here because that's what we need to really focus on. So you would find out that the probability of B multiplied by the probability of C would be equal to the probability of B and C. So this is really what we have to look for. We need to look for the probability of B, the probability of C, and the probability of B and C. Okay, so let's start off with the probability of B. So, like you would have seen in that video on Venn diagrams, the probability of B is the entire circle of B. Everything that is included here is the probability of B. This is not excluding intersections like probability of A and B, because the probability of B is included here as well. Okay, so this entire thing gives you the probability of B. So if we add up all these values, we will get the probability of B. So when I put that down onto the calculator, I get 0.643. So that is the probability of B. So the probability of B is 0.643. And we need to now multiply this by the probability of C. Now the probability of C we would also get by taking the entire circle of C, because everything here includes the probability of C. So we'd add all these numbers up and we get the probability of C. And I get 0.56. Okay, so I've also just decided to write it on the side as well. So that is 0.56. So that's times 0.56. Then lastly, we have to find the probability of B and C. So what is the probability of B and C? Okay, so probability of B and C, looking in your Venn diagram, that is the intersection of B and C. Now look at those two circles. Where do they intersect? They intersect all through here. That is the intersection of B and C. Okay, so you have to take these two numbers and add them because they are the probability of B and C. Though this one has the probability of A in it, it's also still the intersection of B and C. So we add these two numbers, 0.16 and 0.2, and that is our probability of B and C. And we get 0.36. So that's 0.36. Okay, so let's see if this actually works out. When we take this and we multiply it, it should be equal to 0.36. So let's multiply those two. So when I get that, when I multiply it out, this is what I get. I get 0.36 basically, because even if you round it off to 2 decimals, it will still just be 0.36. Okay, and this is equal to 0.36. So that means that the probability of B multiplied by the probability of C really does give us the probability of B and C. And so therefore, it means that events B and C are independent. Okay, and that is it for 10.1.3, and that is really it for 10.1. Then we move on to the 10.2 questions. Okay, so 10.2 says, a 4-digit code is required to open a combination lock. The code must be even numbered and may not contain the digits 0 and 1. Digits may not be repeated. And the question is, how many possible 4-digit combinations are there to open the lock? Okay, so a 4-digit code. It's a code, so it's including numbers. The numbers that you're going to have on any number keypad would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. These are the type of numbers that you're going to find on a keypad. But then now we have to look at the restrictions that they make in here. First of all, they tell us that this code has 4 digits. So we keep in 4 places, 4 digits that it has. And now they also tell us that the code must be even numbered. So the codes that we're going to have, it must be even numbered. So in order to make a number to be even, you just have to make sure that the last digit is even. Okay, so if the last digit is a number that can be divided by 2, then the whole number will be even. So that whole code must be even. So it means at the end, right, we must have an even number. Okay, but let's also just see the other restrictions they put. They also said that, and the code may not contain the digits 0 and 1. Okay, so 0 and 1 must not be there, meaning I cannot use 1, I cannot use 0. So I'm down to 1, 2, 3, 4, 5, 6, 7, 8 numbers to use from. Okay, and the digits may not be repeated. So you also cannot repeat. So to understand this, just think about a scenario where you can repeat codes. So in a normal trackpad where you have like 10 numbers, if they said the numbers can be repeated and they didn't put any restrictions, then we would simply just say, okay, the number of choices for the first digit. So down here, I'm going to be putting down the choices. The number of choices for the first digit would just be 10. This is like in a situation where nothing has been restricted and you're allowed to repeat. I just want you to see this so that you can understand what's going on here. So you'd say, okay, for the first digit, I have 10 options. I can take any of these numbers. Then you basically will always multiply our choices. So a simple explanation for why we multiply the choices is a scenario where, let's say you have bread and then you have 2 things to put on the bread. You can either put cheese or you can put eggs. So in this case, you see, you have bread and you have 2 things to put on the bread. So cheese or eggs. Here, you only have one category, bread. And you have to mix this with either cheese or eggs. There's 2 categories. To find out the amount of sandwiches that you can make, you would say 1 times 2, which is 2 sandwiches, which makes sense because you can either make bread with cheese or you can make bread with eggs. Okay, so that's the reason we multiply. Okay, so the first digit, we have 10 choices. The second digit, this is in a case that it's not repeated, would have 10 choices. Third, 10 choices. And this would also have 10, right? But now we have to take into account the restrictions that are being made here. This is not what we're going to have, unfortunately, because they put restrictions and they also said it cannot be repeated. Okay, so now let's look at a scenario where there is no repetition, no repeat. You cannot repeat here. Then for the first choice, you would have 10 choices. So remember, this is not this scenario. This is another scenario where I'm not putting any restrictions on the numbers you can or cannot use. Then for the second choice, because you cannot repeat the number that was used here, you would have 9 choices. And then for the third choice, you cannot repeat the number that was used in any of these. You would have 8 choices and then 7 choices. Okay, so this is a scenario without any restriction, but you're also just not allowed to repeat. Now let's look at the situation that we have here. We know that on this keypad, we cannot use 1, we cannot use 0. So we only have 8 numbers to use. But now they have placed a restriction on the way the code should look. They said that this code must be even numbered. For a code to be even numbered, you have to make sure the last digit is an even number. Meaning, the only types of numbers you can use at the end are even numbers, which are 2, 4, 6, and 8. Those are the only numbers that you're allowed to use on here. So now already, for the last digit, you only have 4 choices to choose from. Okay, now remember, they mentioned that they cannot be repeated. So if I was going to the first choice, just to see what is going to be put here, remember that we have 8 options to use. We have 1, 3, 4, 5, 6, 7, 8, and 9. We have 8 choices, but we know that we cannot repeat. So one number is going to be put here out of these 4 numbers. But because one number has been used here already, I have to cut this down to 7 choices. I can only have 7 choices in codes that I can use here. Okay, because one of that is being used. Then in the second place, we would only be able to use 6 numbers, only 6 choices that we have here. Okay, because of this one that is already placed down and one of these numbers that will be placed down. And then in the third place, you only have 5 choices. Okay, and then of course we'll multiply that. So start with that restriction because you know that only these types of numbers can be used here. So this is 7 times 6 times 5 times 4, and let's see what that gives us. So that is a total of 840 combinations that we can make. Okay, so that is how that question is solved. And then we move on to the last question of this paper. And now we are on the last question. And the last question says, we have to calculate the probability that you will open the lock at the first attempt if it is given that the code is greater than 5,000 and the third digit is 2. Another restriction has been made here. So we're still using the above restriction, everything here, but then now the third number has to be 2 and the code itself needs to be greater than 5,000. Okay, so first of all, let's see the pool of numbers that we're allowed to use. So here, the first number, right, since it needs to be greater than 5,000, we're going to think about it like this. The type of numbers you're allowed to put down in the first place, in the first digit, will be numbers like 5, 6, 7, 8, and 9. So that it can be greater than 5,000. The code will be greater than 5,000. So this is your first digit. And then we also have to take into account that they also said now that the third digit has to be 2. So we have a second digit and the third digit. So digit 3 has to be 2. Okay, so that one is just set. We cannot change that. Well, and remember the last digit in the information that they gave us above, they told us that it needs to always be even, right? That the number must always be even. So we're still keeping that. Here we were allowed to use 2, 4, 6, and 8. So it means now for the fourth digit, for the last digit, we are only allowed to use, because you see the third digit has to be 2 no matter what. Meaning now we're only allowed to use 4, 6, and 8. Okay, so this is what the bigger pool looks like, but we still need to look deeply at this and just make sure that there isn't any repetition, because they also said there shouldn't be any repetition. So this is our digit 2. Okay, so I'm just going to look at this as the bigger picture. Okay, So you see the issue with this, the reason I can't just go on and say, okay, numbers that I can use here, 1, 2, 3, 4, 5, 5 numbers. The reason I don't think we can do that is because look carefully at this. If you're allowed to use 5, 6, 7, and 8 and 9, right? But you're not allowed to repeat. If you do that, there may be a scenario where you use 6 and then you end with 6. Or a scenario where you start with 8 and then you end up with 8, which is wrong because they said no repetition must happen. So we actually need to separate this. Okay, we need to find certain combinations separately. So we can first of all start by trying to separate them according to how they would end up occurring at the same time. We don't want them to occur at the same time. So if we have to do that, how about we see the fact that the problems here is if we end up starting with 6 and ending and starting with 8. These are the two problems here. Because in these scenarios, you could have situations where you end up ending with 6 or ending with 8. So let's find, first of all, the bigger one first. Let's find the scenarios where we are allowed to start with 5, 7, and 9. How about we look at these first? Okay, so in the case that we're allowed to start with 5, 7, and 9, this would be the situation. This is the first digit that we have. You're allowed to use 5, you're allowed to use 7, and you're allowed to use 9. Then they already told us that the third digit must be 2. So that's the case there. Now, if we start with 5, 7, and 9, what should the last digit be? Okay, remember they must be even numbers. Here, as you can see, 5, 7, and 9, and 4, 6, and 8, they're not the same numbers. Okay, so in this scenario, we will not have a repetition here. So we are allowed to use the numbers 4, 6, and 8 because you see, it's not going to mix with that. You're not going to end up starting with the same number and ending with that same number here. So there's no repetition there. So here we're allowed to use this. Okay, so let's think about what the third number, the third digit should be. The third digit can basically be any out of the 8 numbers. But now we have to think about the fact that right now, these are the codes that we're looking at. In the situation that we're looking at one code, you have put down one number here out of these 3 numbers. You have put down the number 2, okay? And then you have put down one of these numbers out of the 3 numbers. Meaning, because you don't want a repetition, you're going to only have how many choices out of the 8 numbers that you used? Well, that's going to be 8 minus the amount of numbers that have already been placed down, which is 1, 2, and 3. We're looking at one situation of one code. So 3 numbers have been placed down, meaning you only have 5 choices here. So if we're looking at the choices, these are just the numbers that we can use. Here in the first place, we're allowed to use 1, 2, 3 numbers. So we have 3 choices. In the third place, we are only allowed to use 2. We only have 1 choice here. And in the last place, we have 1, 2, 3 choices of numbers we can use. So you see that in the second place, we're allowed to use 5 choices because we are taking into account that this is one code, right? We're pretending this is one code, that one of these numbers have been put down, this 2 is down, and one of these numbers have been put down. So seeing that 3 numbers have been put down, you only have 5 choices remaining to choose from. So there are 5 choices here. So again, you would multiply these numbers and you would get your answer. But then we're not done because that deals with this part, the situations where we start with 7, 5, and 9. Okay, 5, 7, and 9. That deals with that. Now, with the combinations starting with 6 or starting with 8, this is how we're going to have to look at it. So let's deal with the one starting with 6. Okay, so if you're starting with the number 6, sorry, let me just be putting the numbers, the keypad numbers in black. So starting with, so I'm saying or here, so that's one situation, or starting with 6, right, as your first digit. It means that since 6 is your first digit, it's the only one that you can use in this scenario, you have one choice here. Then in the second digit, how many numbers can we use? We can't really deal with that yet. Let's deal with the fact that we know that you must have a 2 in the third place. So you must have 2 in the third place, meaning you have only one choice here. Then in the last place, now you see this is where you really need to take note of this. If you started with 6, you cannot end with 6, meaning in this scenario, in the last place, you're only allowed to end with 4 and 8. So how many choices of numbers do you have here? You have 2 choices. So remember, all of these are being multiplied by each other. Now, in the third place, how many choices would you have? Well, it's still the same situation because you're thinking about the fact that that keypad, when they restricted it, we only have 8 choices, numbers from 2 to 9, basically, right? So out of the 8 choices, we're looking at this as a scenario of one code. One number has been placed down here, one number will be placed down here, and one number will also be placed down here out of these 2 numbers. So 3 numbers have been placed down in your code. How many numbers do you have to use here? You have 5 numbers left. Okay, there. So we have 5 choices here. So that is the scenario starting with 6. We're done with that. Now let's deal with the scenario starting with 8. Or we could have a one starting with the number 8. Again, let's look at the third choice. You have to have a 2 in the third choice. So here, starting with 8, you have 1 choice for the first position. For the third position, you have 1 choice. But now let's look at what this last position should be. We should have even numbers like these ones here. But because we started with 8, we cannot end with 8. We have to end with either 4 or 6. So it means that we have the options 4 or 6. You have 2 options here. Likewise, again, to find that second position, we are saying we had 8 numbers. 3 numbers have been placed down. Okay, we cannot put 2 numbers at the same time. They go one after each other, one by one. So minus 3 is equal to 5. So we have 5 choices in the second position. So if we multiply all of these, we'll get our answers. So you see, if you take all of that, multiply it, you get your answer. You will add it to all of these multiplied and add it to all of these multiplied. So that would give us the total amount, not the probability yet. So let's go ahead and do that. So 3 times 5 times 1 times 3. And the first one gives us 45. So write that down. We have 45 here. And then 1 times 5 times 1 times 2, which you can see that gives you 10 because the ones really just stay 1. So that's 10. And then here we also get 10. So really, all of this, it would really just be 45 plus 10 plus 10, which would be 65. So in total, the amount of combinations you can create using these restrictions is 65. But we need to make sure we answer their question. Their question is calculate the probability that you will open the lock at the first attempt, right? So you're opening the lock the first time. What is the probability that you're going to open the lock and it's going to have these properties, okay? Where the code is greater than 5,000 and the third digit is 2. We found out that possibility that there's 65 combinations that we're going to have. But now this needs to be a probability. So you need to put it over the total amount of outcomes. So this over the total amount of outcomes. The total amount of outcomes would come from the first question really, because the first question gave us the restrictions that you were allowed to use. And it just asked how many possible 4-digit combinations are there to open the lock. So in total, these are the amount of combinations we can use to open the lock. So it's out of these total. So we're taking that out of 840. So 65 over 840, that will be the probability. So 65 over 840, and let's see what that gives us. Okay, and this is what I get. I'm not really saying you can say the probability of, but you see the restrictions they gave was a lot. So if you like, you can just say the probability is, then you say the answer. So this is what we have. It is 13 over 168, which you can leave as a fraction. You can put as a decimal. It will still be fine. I like to actually leave the answer as a fraction because I feel like it's just more put together and not rounded off. Okay, so that would be it. You can also leave it as a percentage. And 10.1 says, a group of people participated in a trial to test a new headache pill. 50% of the participants received a headache pill. Then 50% of the participants received a sugar pill. Then 2 out of 5 receiving the headache pill were not cured. Okay, so out of the headache, not cured was 2 out of 5. They received the headache pill. And then 3 out of 10 of the group receiving the sugar pill were cured. Okay, so the first question, they want us to represent the given information on a tree diagram. Indicate on your diagram the probability associated with each branch as well as the outcomes. So they just want you to draw the entire tree diagram. Okay, so this study, we have a group of people and they're testing a new headache pill. 50% received a headache pill, 50% received a sugar pill. Okay, so headache pill and sugar pill. Those are the two branches that we have first. So I just call this one HP for headache pill and SP for sugar pill. So 50%, that is a half as a fraction. They got the headache pill and a half of that group got the sugar pill. Then they're saying 2 out of 5 of the group of people receiving the headache pill were not cured. So out of these people receiving headache pills, there were people who were not cured. Okay, so it means that we have two criteria as well. You can either get cured or not cured. So I'm going to put not cured. Okay, NC. That was the 2 out of 5 people. Then they also tell us that 3 out of 10 of the people receiving the sugar pill were cured. So I can't put that here. That's headache pill. The people who got the sugar pill, 3 out of 10 of them were cured. So I would just put 1. This branch is for not cured. But the ones that were cured was 3 out of 10. So it means that we can just find these ones. We can find here in the people who took the headache pill, we can find the people who were cured. Okay, and the amount of people that will be cured, not really the amounts, just the fraction of people. If 2 out of 5 people were not cured, then it means that 3 out of 5 people were cured. So that when you add them, they make up 5 out of 5 people. Okay, so here, the people who were not cured, if 3 out of 10 people were cured, then it means that 7 out of 10 people were not cured. This would be your tree diagram and all the probabilities associated with the branches as well. Okay, so they say indicate you have to show the probability associated with each branch. So like, for example, headache pill, it's half. Or from the headache pill, the people who were cured, it's 3 out of 5. Those will be the probabilities associated with each branch. But then they also say as well as the outcomes. So I guess we also have to show those outcomes on the side. Okay, you might hear some background sound, but it's because it's raining. Please excuse the background sound. Okay, so I'm going to put the outcomes as well on this side. Okay, so the first outcome, we're looking at the probability of people who received the headache pill and were not cured. Okay, so we're looking for people who received headache pill and were not cured. And that would be, you would have to take that half and multiply it by the 2 over 5. Okay, and that would be equal to, okay, that's going to be 1 over 5 because you can see that the 2 and 2's will cancel. So 1 over 5. And then we have to look at the people who received the headache pill and were cured. So headache pill and cured. And so we're going to take that half and multiply it by the 3 over 5. So 3 over 5. Let me see if I can guess this one. It's going to be 3 over 10. Okay, so no need to put it on the calculator. Okay, so this is going to be 1 times 3, that is 3, over 2 times 5, that is 10. Okay, then we're going to look at people. So we're done with the people who took the headache pill. Then the people who took sugar pill. So sugar pill and were not cured. So the sugar pill and not cured. And that would be a half multiplied by 7 out of 10. Okay, to multiply this, I'm just going to cancel. No, I can't cancel. 1 times 7 is 7 over 20. Okay, then the people who took the sugar pill and were cured. So, and cured, that would be the half multiplied by the 3 out of 10, which is equal to 3 over 20. Okay, so those would be the outcomes of everything as well. So that is for 3 marks. Yeah, that looks like a lot of work for 3 marks. But okay, moving on. And then question 10.1.2, next question says, determine the probability that a person chosen at random from the group will not be cured. So whether they took the sugar pill or they took the headache pill, We just want the probability of people who will not be cured. So that's what we're going to be looking for. As long as they were not cured, you're going to take that. So looking at the outcomes, look at what we're going to take. We're going to have to take that. These are people who took the headache pill and were not cured. And we're going to have to take this. This would be people who took the sugar pill and were not cured. We have to take both of these because these people, regardless of whatever pill they took, they were not cured. That's what they asked for, people who were not cured. Okay, so this is really how we're looking at it. In other words, if we just use words to say it, we're looking for people who were not cured. So they can either be people who took the headache pill and were not cured, or it could be people who took the sugar pill and were not cured. Notice the word or was used. When we say or, it means to add. And you can look at it like this. Let's say we have a coin and this coin has a head and tails. So if I say, what is the probability that you're going to flip this coin and land on heads? Then since it's a coin, it's just going to be 1 out of 2 because there's one head out of the 2 faces that are on this coin. But if I said, what is the probability that you're going to get heads or tails? That's going to land on heads or tails. You're only going to ever land on either heads or tails. So it's 100% chance. And the reason why is because we said the half plus the half. And that gave you 2 over 2, which is 1 or 100%. Okay, so that's why when you see the word or, you need to add. So we're looking at the probability of people who took the headache pill and were not cured. And we adding that, okay, to the people who took the sugar pill and were not cured. Okay, and we already have these numbers. So the people who took the headache pill and not cured, that is 1 out of 5 in total when we multiply headache pill and not cured. So 1 out of 5 plus 7 out of 20. So 7 over 20 plus 7 over 20. And let's see what we get. And if you put that on the calculator, then it gives you 11 over 20. Okay, so that's that answer there. And moving on to the next question. So question 10.2, we have 3 events A, B, and C are considered. Probability of A is 2 over 5, the probability of B is 1 over 4, and the probability of A or B is 13 over 20. So 10.2.1 says, are events A and B mutually exclusive? Support your answer with the necessary calculations. So they want to know if they are mutually exclusive. So the thing about mutually exclusive events, since they're speaking about A and B, for events to be mutually exclusive, then the probability of A and B would be equal to 0. And this really just means that there is no intersection. Because remember, mutually exclusive events, they do not intersect. So in a Venn diagram, they look like this. No intersection. So let's think about a formula that we can have that will include A and B. So where we can actually solve for A and B. They told us about the probability of A or B. The formula for this, the probability of A or B, is equal to the probability of A plus the probability of B minus the probability of A and B. So as you can see, we have this now. We have the probability of A and B. So let's go ahead and put down what we have. Probability of A or B is 13 over 20. Is equal to the probability of, I think I can write that smaller, 13 over 20 is equal to the probability of A, which is 2 over 5, plus the probability of B, which is 1 over 4, minus the probability of A and B. Okay, so in this, I'm going to take this over just to make it positive. It's negative right now, but if we put it over the equal to sign, it will be positive. So now that is the probability of A and B. Okay, it's negative because of the minus in front of it. And it's equal to, if we add these two together, so 2 over 5 and then plus 1 over 4, that gives us 13 over 20. So this is equal to just 13 over 20. And then, remember, that's just this part. Then we also have a 13 over 20 here. We can take that over and that becomes a minus 13 over 20. So it really just means now that the probability of A and B is going to be equal to 0. And there we go. So if the probability of A and B is equal to 0, then it means that A and B are mutually exclusive. Okay, so it would mean that those events are mutually exclusive. So mutually exclusive events. Okay, so that is the first one. We've proven that they are mutually exclusive. The next question says, determine the probability of only C if it is further given that the probability of A or C is 7 over 10, probability of A and C is 2 over 5, and 2 times the probability of B and C is equal to the probability of A and C. Okay, so there's a lot of information they give us here, and for us to know how we need to use it, let's focus on what we actually need to do. We need to find out what the probability of only C is. That's the goal. So let's focus on that. How can we find the probability of only C? Well, a good way to be able to look at this information is by looking at it in a Venn diagram. So the good thing about this, we already know what the probability of A is, we know the probability of B is, and we even know that A and B are mutually exclusive. So as you can see, they're only mentioning 3 events. We have A, B, and we have C. We know that the circle of A and the circle of B will not intersect because they are mutually exclusive events. So they'll look something like that. But now let's see if A and C are going to intersect. Notice they say that the probability of A and C is 2 over 5. Meaning there is an intersection between the circle of A and the circle of C. But then they also say 2 times the probability of B and C is equal to the probability of A and C. And you see that the probability of A and C has a number. So since we can see there's also an intersection here with the probability of B and C, it means that the circle of C also intersects with B. So the circle of C kind of looks like this. So it's a circle that will intersect with B and A because it has intersections with them. Okay, so that's what this looks like. Now, what they want us to find is the probability of only C, meaning not the entire circle of C, but just only C. You see, if you take the entire circle of C, if you take everything in here, notice that that will include that little part, but that is part of A. We cannot take A, anything in A. And if we take this entire circle, it will also include this little part, which is part of B. We need to take the ones that is only C. So we're only going to take these ones. We're going to take this part, excluding those little pieces. So excluding those intersections. Okay, so how can we actually find out this? What is a formula, an equation that we can construct to find out what this is? Well, we have the circle of C. We can focus on the fact that we have the entire circle of C. If we could find out, so I want the probability of only C. If we could find out what the entire probability of C is, the probability of C is, and then we subtract that by this intersection over here, that is the probability of A and C. And then we also subtract that by this circle here, the probability of B and C. Then it will leave us with the probability of only C, that shaded part in purple. Okay, so let's go ahead and do that. So we're going to look for the probability of C. Let's see if we have that. So notice they don't really tell us the probability of C, although they do mention things that have the probability of C in them. They tell us about the probability of A or C, and they also tell us about the probability of A and C. So we can use the OR rules formula to actually find this one by saying the probability of A or C is equal to the probability of A plus the probability of C, then minus the probability of A and C. Okay, so let's look at what we have. So remember, the whole goal of this is to find this, the probability of C. So the probability of A or C, that is equal to 7 over 10. So we can say 7 over 10 is equal to the probability of A, because we need to add that now. Probability of A, we have that. They said the probability of A was 2 over 5. So that is 2 over 5 plus the probability of C, that's what we're looking for, then minus the probability of A and C, which they told us is 2 over 5. So that is 2 over 5. Okay, so looking at this equation, you can see that we have 2 over 5 minus 2 over 5, and so those would cancel. And now we have the probability of C is finally just equal to 7 over 10. Okay, so now we have the probability of C, we have this one. Now let's look for the probability of A and C. Well, we have that. They already told us that was 2 over 5. So we have the probability of A and C. So lastly, we need to find the probability of B and C. Okay, so they told us something about B and C. They told us that 2 times the probability of B and C is equal to the probability of A and C. So let's go ahead and use that equation. Okay, I'm also just going to move everything up to here. Okay, so I'm looking for this one. So let's use that formula. We know 2 times the probability of B and C was equal to the probability of A and C. But we already know what the probability of A and C is. That is 2 over 5. So it's equal to 2 over 5. So we just have to solve for the probability of B and C by getting rid of this 2. And so we'll just divide both sides of the equation by 2. And so that means the probability of B and C would be equal to this 2 over 5. And then we can just say divided by 2. And so that gives us 1 over 5. So 1 over 5 as the probability of B and C. So now we have the probability of B and C. We have everything we need to find the probability of only C. So I'm going to rewrite this formula and let's just substitute where we need to. Okay, so let's see, the probability of only C would be equal to the probability of C, which is the 7 over 10 that we have, so 7 over 10, minus the probability of A and C, which we also have that. Probability of A and C, that was the 2 over 5. Okay, so the 2 over 5, and then minus the probability of B and C, which is 1 over 5. So let's go ahead and see what we get. Okay, so this is what we get. We get 1 over 10. So 1 over 10, that is the probability of only C. Okay, so you see ways that you can find these answers. You're going to have to construct equations. Don't get lost or confused by the amount of information they put. Just try to think in the direction of, let me construct a way to find this answer. And so you will start to see that the information that they put down are actually things that you need to get to your answer. Okay, so the next question we have is this. They ask us to determine the probability that events A, B, or C do not occur or take place. Okay, so how do we find the probability that they will not take place? Okay, so to explain this, let me bring this Venn diagram back down. So look at what they're asking for. They want the probability that events A, B, or C do not take place. So none of them must take place. This is how you can look at it. We don't want A, we don't want B, we don't want C. So if you look at that, what is remaining in this Venn diagram? It is whatever is outside the Venn diagram. So it's that event where they're neither A nor B nor C. And I'm going to go ahead and just call that X. And now how do we actually find this value of X? Well, if you look at a Venn diagram, all the events in the Venn diagram, remember that they are giving us these probabilities as fractions, right? So if they're giving it to us as fractions, everything in the Venn diagram, when you add it up, it will add up to 1. It's like one whole. In other words, 100%. So it's 100% of all the data in this study, in this Venn diagram. So in order to find X, we're going to find X by actually saying it would be equal to 1 minus the probability of A or B or C. Okay, that's how we're going to find it. And so from this, you can already see now that all we need to find is what is the probability of A or B or C. So this is how we'd find the probability of A or B or C. We're going to take the entire circle of A. So remember that the word or means to add. So we're adding all these probabilities together. We're taking the entire circle of A and we're going to add that to the entire circle of B. But let's start with C just so that you can see what's going on here. We're adding that to the entire circle of C. But then look at the problem here. You took everything that was inside the circle of A, right? Including that little piece, that intersection. That's included in the circle of A. And then you added it to the circle of C. Also includes that intersection as well. Now, you see the problem with that is that you just added that intersection twice. And this is the reason why in the OR rule, when we take the probability of A or C, for example, we say the entire circle of A plus the entire circle of C, And then we have to say minus that intersection. It's not because we're trying to remove the intersection. It's because you added the intersection twice. When you said the entire circle of A, it includes the intersection, plus the entire circle of C, it includes the intersection as well. And so you see that is added twice, and that's why we have to say minus the probability of A and C. That's what that rule is meant to do. Okay, so when we're actually finding this, we're just trying to find the probability of A or B or C. I'm going to just sum it up all together here. So that is going to be made up of the probability of A plus the probability of C. Then, of course, you have the minus the intersection, but I'm going to do that at the end. Then we also have to add the probability of B as well. Now, you see, the problem with this is if I add the probability of B, when I spoke about the entire circle of C, that included that intersection by B. So if I add again the entire probability of B, that is also included that intersection. That's why I also have to say minus the probability of B and C as well. Okay, so I will add the probability of B, but then now I need to remove those intersections that have been added twice. So minus the probability of the A and C. So A and C, and then minus this one that has been added twice as well. So minus the probability of B and C. And that would give us the entire probability of A, B, and C, all of those circles. So you see in this, I don't have to say minus the probability of A and B because there is no intersection between those two circles. Okay, so let's go ahead and see, do we actually have this? And they didn't really give us more information, so it means everything is probably here. So it's equal to the probability of A. We have that. They told us that and in the beginning. So probability of A was 2 over 5. We have that. So we can just say that is 2 over 5. Then plus the probability of C. The probability of C, we also have that. We actually had to find that. Probability of C is 7 over 10. So that is 7 over 10. Then plus the probability of B. The probability of B, do we have that? Yes, we had that from the beginning. So probability of B, that's 1 over 4. So 1 over 4. Then we have to say minus the probability of A and C, which that one, I think that was 2 over 5 we had. Yes, 2 over 5 probability of A and C. So minus 2 over 5. And then lastly, minus the probability of B and C, which we simplified. Yes, that probability is 1 over 5. So minus 1 over 5. And let's go ahead and see what that is going to give us. And we get a 3 over 4 as the probability of A or B or C. Then remember to find the probability of not A or B or C, that is that X over there. So that would be equal to 1 minus the probability of all of that A or B or C, which we now know is 3 over 4. So minus 3 over 4. So that would be equal to, it's probably going to be a 1 over 4. So it's like 4 over 4 minus 3 over 4. 1 over 4. So you can answer them in a way that what you're saying is actually written properly, kind of like written in the correct notation. So I'm just going to say it's the probability of A, not A, I mean, or not B, or not C. So it's like the complement of it is equal to 1 over 4. Okay, so that's our final answer there. Then moving on to the next question. And now we're on question 10.3. And question 10.3 says 7 friends, which is made up of 4 boys and 3 girls, want to stand in a straight line next to each other to take a photo. 10.3.1. How many ways can the 3 girls stand next to each other in the photo? Okay, so the 3 girls need to stand next to each other in the photo. Okay, so I'm just going to make these symbols. For the boys, I'm going to put that, and for the girls, I'm going to put that. So let's represent these 7 friends. These are the 7 friends, and the question is asking in how many ways can the 3 girls stand next to each other in the photo. So notice that a group has been created here. When we create groups in the counting principles, this is what we're doing. We're making these one group. So no matter where they stand, they need to be just one group on their own. They need to always stay together. This is what I mean by that. So, for example, this is what I mean by that. You see this one boy, he could be standing here on the right of them. We could even have a case where two boys maybe stand on the right of them. As long as these three girls are together, we have created this one group. And this is how I like to work with groups. So I'm saying that these three girls are together. They don't necessarily have to be at the back, they can also be at the front. So if they have to be in one group together, we're going to look at it like this. I'm going to say the amount of ways that these three girls on their own can stand like this, because remember, there are three different girls. Yes, they're standing together, but this first girl doesn't have to be standing only in this position. She could also stand in the second position or the third position. The second girl, after the first one is standing, she has two positions to stand at. And the last girl can also just stand in this last position. So to find out the amount of ways that they can be seated, even though they are sitting together right now, we would have to say 3 factorial for that. So that's just for inside that group. They don't have to be sitting in this order. Okay, then the rest. Remember, they didn't say that the boys have to be seated together. And that's why I said that the boys, for example, this one boy can be sitting in front of the girls. Okay, so the boys don't have to be seated together. So this is what is really going on. I'm going to pretend that each boy is a group of his own. So the amount of ways that this one boy can be seated, I'll just call that 1 factorial, which is 1. But I'm just keeping it as factorial because for the sake of understanding in groups, I just want you to remember that we're constantly using factorials. And remember, we're multiplying these, okay, to find the amount of ways that they can be standing like this. Then this other boy, I'm also going to treat him as one group on his own, 1 factorial and 1 factorial and another 1 factorial. And remember, we are multiplying these. After that, remember that I'm just saying that this one boy, the amount of ways that he can be seated on his own like this is just one way. But then I can't just do that. The thing is, we have created a group for the girls, but the boys should still be allowed to sit in anywhere as long as they're not in between the girls. Meaning, this boy can sit here, for example. Or it could be a case where this boy can sit here instead, or even in between them. Now, to allow them to be able to move around freely, and even the girls themselves, because the girls don't have to be seated here. They could be seated in between, for example, these two boys, or in between these, okay? Now, to allow them to freely move around like that, we're going to multiply it by the amount of groups that have been created. So, the amount of groups that have been created would be, this is the first group, this one boy will make up the second group, third group, fourth group, and fifth group. So we're seeing it as there are 5 groups. So we're timesing that by 5 factorial so that these ones can also move around. So these group of girls, for example, they don't have to be seated here. They can be seated all the way here. Okay. So that's what I'm timesing by the amount of groups factorial that they can be seated in. And so let's see what this gives. So you can simplify this. The 1 factorials, they really just make up 1. And when ones get multiplied, it gives you 1. If 1 gets multiplied by 5 factorial, it will just stay 5 factorial. So we have 3 factorial multiplied by 5 factorial, and that would be equal to, then we can just find out what that gives us. So remember the factorial button, we just say 3 and then you say shift and that, okay, factorial. Then multiply by 5 factorial, and that gives us 720. So there are 720 ways that these friends can be standing in as long as 3 girls have to be seated together. Okay, moving on to the next question, and this is the last question. The last question says 10.3.2. In the next photo, determine the probability that Selwyn, a boy, and Lindiwe, a girl, okay, will not stand next to each other in the photo. So the probability that they will not stand next to each other. So something you need to take note of, first of all, is that they are asking you for the probability. So not just the amount of ways, but the probability. Okay, so probability would be a fraction, for example. So let's just find out what that denominator of the fraction is. Like, for example, what if this question was, what is the probability that 3 girls will stand next to each other? Then we would have taken this, right, 720, and we would have put it over what? Well, you put this over the total amount of ways that the friends can be standing next to each other if they were not grouped in any way at all. And the ways that they'll be standing next to each other without any groups being made would be the amount of people that they are. There are 7 friends. So that would be 7 factorial. Okay, so I just want you to see that total, that denominator of whatever our probability will be is 7 factorial. Okay, so looking at this now, since they want us to find out the probability of the ways that this boy and the girl will not stand next to each other, how about we find out the amount of ways that they can stand next to each other? Then we'll be able to subtract that from the total ways that all these friends can be standing in this photo if no groups were being created. So let's find out the total ways that Lindiwe and Selwyn can actually be standing next to each other. So let me put down the illustration of the friends standing next to each other. Okay, so here are the 7 friends, and what we have to do is make Lindiwe and Selwyn sit together, or rather stand together. Okay, so here are the 7 friends, and remember what we're trying to find out is the amount of ways, we'll talk about the probability at the end, that this boy and the girl will stand together. So will stand together. So to find out that probability, let's go ahead and group them together. So we need to make sure that Selwyn and Lindiwe are standing together. So one group has been made between them. They're going to be standing together like that. And then everybody else, I'm going to consider them as an individual group of their own. So the amount of ways that they can be standing together despite the fact that they have to be one group would be 2 factorial. And if you check that on the calculator, it's really just 2 ways. And the reason why is because the way they can be standing like this in a group is Selwyn can be standing first, then Lindiwe, or it could be a case where Lindiwe is standing first and then Selwyn. So you see that's 2 ways in total that they can be standing even as a group. Then we're going to look at everybody else as a group. So you make up one group, that makes up one group, and everybody else makes up one group. Okay, and remember we're multiplying all of these numbers. Then you have to multiply by the amount of groups factorial that has been created. Because of this, Lindiwe and Selwyn are one group, and then each person is a group of their own. So that's 1, 2, 3, 4, 5, 6 groups have been created. So I'm multiplying it by 6 factorial. That way everybody else can move around. For example, this boy over here doesn't necessarily have to stand here. He can also stand in front of Selwyn and Lindiwe, or you could stand in between them. Okay, so that is to make sure it's not restricted like this. They don't have to be standing in this order. Okay, so what is that going to give? We can simplify that. This is going to be the 2 factorial, and of course the 1s just become 1, and 1 multiplied by anything really just stays the same. So multiply by 6 factorial. Okay, so let's go ahead and see what this will give. And remember, this is the amount of ways that they will stand together. So for that, I get 144 ways that they will stand together. Okay, now because of that, we'll be able to find out the probability of ways that they will not stand together. So if this is the amount of ways they will stand together, how much ways will they not stand together? Well, to find that out, we're going to find out the total amount of ways that everybody can just stand without any groups being created. And that would be the fact that there are 7 friends. That would be 7 factorial. That would be the total amount of ways they can stand without groups being created or any restrictions being made. Then we're going to minus that by the amount of ways that they will be able to stand together, where Lindiwe and Selwyn are standing together. That was 144 ways. So minus 144 ways, and that will give us the amount of ways that Lindiwe and Selwyn will not stand together. Okay, so it's really just the total ways that everybody can be standing minus the amount of ways that they will stand together. That will give you the ways that they will not be standing together. And when I calculate that, I get 3,600 ways. Okay, now remember this final answer, it needs to be as a probability because that's what they asked for. So the probability that Selwyn and Lindiwe will not stand together would be this. This will be equal to this 3,600 ways over the total amount of ways that the friends can be standing if there were no restrictions made. And that would be the 7 factorial. That's the total amount of ways they can stand. So when we put this as a fraction, that should give us that probability. And so 3,600 over 7 factorial gives us 5 over 7. So 5 over 7 is our final answer. We are finally on the last video for this paper, and this is question 11 and question 12. So question 11 says 11.1, machine A and machine B are two different coin pressing machines that operate at the same time. Then they tell us that the probability that machine A only presses a 5 rand coin is X, and the probability that machine B only presses the 5 rand coin is 0.3. Okay, so we have that, as you can see. The probability that both machines press 5 rand coins at the same time is 0.1. So they've represented this in a Venn diagram. So this is just a representation of those probabilities as a Venn diagram. And the first question is, if A and B are independent events, determine the values of X and Y. Okay, so we can start off with X. X is part of the circles here. See, they told us if they are independent, right? How do we actually find the value of X? So we need to understand something about independent events. See, independent events, if you take the probability of A and B, which we do have, okay, that is the intersection of A and B, it should be equal to the probability of A multiplied by the probability of B. That's how independent events work. So let's go ahead and use this and form our equation. So the probability of A and B is that intersection of both events, which is 0.1. And then this should be equal to the probability of A. So this is what they mean by the probability of A. You see, the probability of A is the entire circle of A. I want you to see that X is the probability of A only, excluding B, so B is not part of it. Likewise, with that 0.3, that's the probability of B only. And then this one includes the probability of both of them occurring at the same time. Okay, so when we're looking for that probability of A, we need to take the X and the 0.1. We need to add those together. So probability of A is equal to that X plus 0.1. And then multiply by the probability of B. The probability of B we'll find by saying the entire circle of B. Okay, so we clearly have to say this 0.1 plus the 0.3, which we know if we add them together, they will give us 0.4. So that's multiplied by 0.4. So this is our equation, and we just need to solve for this. Okay, so please notice that a binomial is multiplying by a one-term expression, a monomial. So what we're going to do there is distribute. So that multiplies to the X and it becomes it becomes 0.4X, and then it multiplies to the 0.1. Okay, so 0.4, you can use your calculator, times 0.1 is going to give you, so it's still positive, it's 0.04. Because it's really like 4 over 10 multiplied by 1 over 10, okay? 10 times 10 is 100, and 4 times 1 is still 4. So as a decimal, that is 0.04, okay? So we have that, and we have 0.1. Okay, so this is what we have. And now we're just solving for X. So let's take the number over. What is 0.1 minus 0.04? Okay, so if you wrote this as 0.10 minus 0.04, then we would see how that actually subtracts. You would be left with 10 minus 4 is 6, so that's 0.6. So that's what we get there, 0.06, okay? When you take the 0.4 over, again, you can use a calculator. So when we take that over and we subtract, we get 0.06. And this is equal to the 0.4x. Then we need to get rid of that 0.4 so we can solve for x. So divide both sides by 0.4, and therefore x is equal to, so we can divide that. Okay, so there we go. Our answer is 0.15. So you do not have to do these calculations manually because you know that you are allowed to use a calculator for this exam. Okay, so we found X and now we still need to find Y. So that is 0.15. We can go ahead and put that in 0.15. Okay, so we have to find Y. And you see where Y is? Y is right on the outside. So it's not included in the circles. So we are at an advantage because these are in decimal form. Because they're in decimal form, think about what everything would add up to if you added everything inside this rectangle. All of it should add up to 1. And the reason it should add up to 1 is because they're really just probabilities, it's the chances of things happening. And altogether, they make up one whole, okay? So it's really, if you add everything, you get 100% of all the probabilities that you have here. So what we're going to do is to find Y, because it's not included in the circle, we can say to find Y, we'll say Y is equal to, you're taking 1, which is everything it should add up to, and you're going to subtract it by everything that is here. So minus the 0.3, the 0.1, and the 0.15. So minus 0.15, minus 0.1, and minus 0.3. And you can use your calculator to find out what this is. And Y is equal to 0.45. Okay, so there we go. So that is the probability that none of these events would occur. Moving on to the next question. The next question, 11.1.2 says, determine the probability that exactly one of the machines is pressing a 5 Rand coin. So let's think about that. They want exactly 1. Let's look at our diagram. When you look at this probability of 0.15, that is the chance of this machine, right, pressing out a 5 Rand coin. But you're thinking about it like this. How many machines is it referring to that is pressing out a 5 Rand coin? Here by 0.15. How many machines is pressing out a 5 Rand coin? It would be one machine, because this is the probability of machine A only, okay, being the one to press out a 5 Rand coin. So this will be included in our answer because this is one machine pressing out a 5 Rand coin. What about 0.1? How many machines here are pressing out the 5 Rand coins really? That would be 2 machines, because this is the intersection of machine A and machine B both pressing out 5 Rand coins. So we cannot take this because it's 2. They want there to be exactly one machine pressing out a 5 Rand coin. And then 0.3, how many machines there? That would be one machine. That is machine B. Okay, that's the probability of only machine B pressing out a 5 Rand coin. So do you see now that the probability of only one machine pressing out a 5 Rand coin can either be this, okay, the 0.15 machine A only, or it could be machine B only. So to give them the answer, we're going to have to add these two probabilities because we're saying either one of them would be correct. So we're adding those together. Okay, so that answer, I don't really think we need to put it in probability format, because how do I say that? Probability of exactly 1. I'll just say 0.15 that we saw there plus the 0.3, which would give us 0.45, because please see that as a 0.15 plus 0. I know it says 3, but you can't just put a decimal of 0 there. So it's 30. So that is why it is 0.45 together. Okay, so that is that answer. Moving on to the next question. Moving on to 11.2. 11.2 says, Wilson takes a driver's test. The probability that he will succeed on his first attempt, okay, very big keyword here when they're speaking about trials or attempts or things, maybe something happening in the first trial and the second trial. So things happening in different positions, okay? You should immediately think about 3 diagrams, okay? So they tell us that the probability that he will succeed on his first attempt is 3/7. So that's very important to just note down, that he will succeed the first time is 3/7. Then they tell us that for each attempt that he redoes the test, the probability of passing increases to 3 over 5. So after the first attempt, right? The first attempt, the probability that he's going to succeed or pass is 3 over 7. Then every other attempt that comes after, his probability now increases to 3 over 5. And the first question is, what is the probability that Wilson will succeed after 2 attempts? Let's go ahead and break down the scenario first before even touching that question. So you see that they said in the first attempt, the probability that he will succeed. Let's actually use the word pass because he can either pass the test or he can fail the test. So what's going on here is Wilson is going for a driver's test, right? And this is his first attempt. He can either pass the test or he can fail the test. So remember, this is the first attempt. They told us that. So remember, they told us the probability that he will succeed, okay, aka pass, we really just mean pass. The probability that he will pass on his first attempt is 3 over 7. So we know the probability he will pass is 3 over 7. So what is the probability that he will fail? That would be 4 over 7, because that is the remaining part, okay, left. If you take, since it's out of 7, there is only 4 parts left. Then, so that is the first attempt specifically. Then they said for each attempt that he redoes the test, the probability of passing increases to 3 over 5. So this is the first attempt. Now, if he takes a test again in the second attempt now, okay, now we're looking at it like this. The probability that he will pass now increases to 3 over 5. Now, the only reason why it's here is because we're looking at these probabilities like this. He can either pass or fail. So we are saying if he passes, the probability that he will pass in the second test would be 3 over 5. So what would be the probability that he's going to fail this? It would be 2 over 5. That's all that's left out of the 5 parts. Then if he fails, remember they say for each attempt that he redoes the test, the probability of passing increases to 3 over 5. So this is always going to be the probability that he's going to pass in each attempt after the first attempt. So the probability that, let's say he failed the first time, the probability that he's going to pass in the second test would still be 3 over 5 again. And the probability that he's going to fail would be the remainder of that. That would be the 2 over 5. Okay, and this will keep going. We can even put a third one as well. So if he passes, okay, the probability that he's going to pass in the third test is again 3 over 5, because they told us every time he redoes this test, the probability of him passing increases to this, not by it, okay, to 3 over 5. So that is what we have there. So increases to that. And then the probability that he fails would have to be 2 over 5. That's what keeps happening. So this is kind of going to get repeated again. I can literally just copy it and paste it here. So if he failed in his second attempt, this is the probability that he'll pass and fail. And then we'd have the same thing here and the same thing here as well. Okay, so this is what we have. We have the first attempt. This is the first attempt. And then this is the second attempt. And this is the third attempt. That's what's going on here. So to be honest, I don't even need, there's some parts that I don't even need to like put here that is just unnecessary. Because if he passes the first test, he doesn't have to even take a test again. We actually need to focus more on the failing, really. But this will still work. You'll see it will still work because it still has everything we need. It just looks more busy. Okay, so the first question is, what is the probability that Wilson will succeed after his second attempt? So let's think about it like this. You see, for Wilson to succeed in his second attempt, he must have failed his first. Because if he passed his first, why would he need to take another test? So with that being said, we know in the first attempt, he needs to fail first. And then in the second attempt, he needs to pass. And that's the only way he's going to succeed in his second attempt. So he fails here first. Then in the second attempt, he needs to pass. So do you see the probabilities we're going to take? And remember, with tree diagrams, you multiply your probabilities across like that. So this is what we're going to take. We're going to take the 4/7 for him to succeed or pass in that second attempt. We're going to take 4/7 multiplied by the 3/5. Okay, because he has to fail the first time for him to even succeed in the second attempt. Okay, so this is what we have, and 3 times 4 is 12, and 7 times 5 is 35. So that would be our answer. Okay, moving on to the next question. Then the second question, 11.2.2 says, determine the probability that Wilson will succeed after 3 attempts. So, which attempts must he fail for him to succeed in the third attempt? He needs to fail attempt 1, fail attempt 2, and then pass in attempt 3 for him to succeed in 3 attempts. Because if he passed attempt 1, why is he writing the test again? Okay, so that's how we're going to look at it. So now we're going to look at it like this. The first attempt, he needs to fail. Okay, so we're going to go with fail. And then the second attempt, he needs to fail again. And then the third attempt, he finally needs to pass. So that's how we're looking at it. You see, it leads to fail. Then we have 2 branches, either pass or fail. So we go to fail. And then 2 branches, either pass or fail, we go to pass. That way he will pass in his third attempt. So let's go ahead and take those values and multiply them. So we are taking the 4/7, we're multiplying it by the 2/5, and then we're multiplying it by the 3/5. So 3/5. And we're going to go ahead and just put that there and find our answer. Okay, so let me go ahead and multiply those out and see what exactly they give us. Okay, we can actually just multiply it. So 2 times 3 is 6, 6 times 4 is 24, and then 7 times 5 is 35, 35 times 5, you can just say 5 times 30 is 150, and then 5 times 5 is 25, so that's 175. So that's over 175. And we know that these don't have anything in common because that has factors of 5 and that has factors of 2. So that would be our answer. That is our final answer there. Okay, and we finally move on to question 12, which is the last part of this paper. Okay, so now we're on question 12. So 12.1 says, when Marge turned 8, her friends Emily, Clara, Corey, Liza, Shirley, and Penny were invited to her birthday party. Marge and her friends sat in a row. Okay, so they sat in a row. Let's just count the amount of friends they are. Okay, so it's Marge, because Marge is with her friends, right? So it's Marge, 1, Emily, Clara, Corey, Liza, Shirley, and Penny. So in total, that's 7 people, okay? Because she has 6 friends. So the question is, in how many ways can they be seated if, first of all, they are seated in alphabetical order? Okay, so a question like this has somewhat shown up in the May to June 2024 paper, okay, in paper 1, probability as well. And with this one, you see, you can either be in alphabetical order or you're not in alphabetical order. So their names, right? I know their names are starting with different letters, but if their names were starting with like A and B and C and D, you can either be in alphabetical order or you're not in alphabetical order. So the amount of ways they can be seated if they are in alphabetical order, because they are different people with different names, is only one way. Okay, because they can either be like this, or if I move this here, do you see now that they are not in alphabetical order anymore? Because we know that C is not supposed to come before A. So that's what I mean by they can either be in alphabetical order or not be in alphabetical order. So there will only be one way for them to be in alphabetical order. That's, of course, if you're looking at alphabetical order as in we need to start from A and then increase from there, like the way the letters go. You could also look at it as alphabetical order but backwards, you see. So like maybe decrease in alphabetical order, like E, D, C, B, A. So you could also look at it like that. So in that case, that would be 2 ways. But I'm just going to say alphabetical order. The standard alphabetical order usually just means A first and then everything else that comes after A. Okay, so that is the answer to that. It's just 1. Then the next question, 12.1.2 says, Emily and Clara do not want to sit next to each other. Okay, so let's just go ahead and represent everybody that is here. So they're all sitting in a row. So there is Marge, there is Emily, Clara, Corey, Liza, Shirley, and Penny. Okay, so 7 people in total. And they tell us that Emily and Clara, for whatever beef they have, don't want to sit next to each other. So we need to make sure these two are not next to each other. So how can we do that? Well, how about we just find out the total probability that we would have if they had to be next to each other, right? And then say the total probability of all the friends just sitting without any restrictions made minus the probability of them being next to each other. So first of all, I'm going to actually group them next to each other, and I'll find out what exactly or how many placements will we have if they are sitting next to each other. Then I will subtract that from the total probability we need to get. Okay, so I'm putting them as one group, meaning Emily and Clara are going to be next to each other. And since they are one group, you see, with counting principles, when you form a group, you call that group the amount of people or the amount of objects that you have and that number, and then you say factorial. And the reason why is because you're looking at this group alone and you're saying, as they are as one group like this, how many ways can they be? Let me actually just put a rectangle. So how many ways can they be seated next to each other in this group? They can either be Emily first and then Clara, so that is one way, or it can be Clara first, then Emily. Okay, so that's 2 ways. So they only have 2 ways to be seated like that. So we just say 2 factorial, okay, which is just 2 times 1. I just like to keep it as factorial. I know that in the case of 2 factorial, it's just 2 though. But this is how we generally work with it. And then everybody else does not have to be a group because nobody else is being grouped. We're only grouping these 2 together. And then, so everyone else is a single person on their own. So what we can do to find out the total ways that they can be seated if Emily and Clara must be seated next to each other, first of all, is this. We're saying 2 factorial and then multiply by, normally, or in my past videos, I know I explained it as treating each person as a group, which works out. But if I treated each person as a group, it would be 1 factorial, and this person is 1 factorial, and 1 factorial, and 1. But the thing is, 1 factorial is still 1. Okay, and when you multiply 1 all through, it still gives you 1. So I don't really have to do that. What I'm going to do now is ensure that each person is allowed to sit in different places, that they don't have to sit exactly where they are seated. For example, Marge can sit here, or she could sit here, okay? Same way, Penny, for example, can either sit here or here, but she cannot sit in between them. That's why we created this group of 2 factorial. Okay, so that's what's going on here. So we're going to technically count how much groups we've created, treating each person as if they were a group of their own, except for Emily and Clara. We're going to go ahead and count them like this. So it's one group, that is one group on its own. That's 2, 3, 4, 5, 6. And so that is 6. And so for that, we say 6 factorial so that they can move around. They don't have to be specifically seated in these positions. The only thing that will happen is that nobody can sit in between Emily and Clara. So that would give us, well, we could find that, or we could actually just go straight away to calculate the answer. So I want you to see that this is the amount of arrangements that we will have if Emily and Clara must be seated next to each other. Okay, so the amount of arrangements for Emily and Clara to not be seated next to each other would work like this. We would take the total ways that everybody can be seated if they were not grouped in any way. And that total way would be the amount of people you have factorial. Okay, you have 7 people. So that's 7 factorial. This is the total ways that everybody can just be seated if no grouping was happening or anything like that. And we can subtract this by the amount of ways that Emily and Clara are seated next to each other. And that would give us the total ways that Emily and Clara are not going to be seated next to each other. So we're subtracting this by, because they've been multiplied, I'll just take it like this, 2 factorial times 6 factorial. And we can go ahead and find this answer. So remember that factorial button. So we say shift and it's that x to the power of -1. Okay, so we're saying minus 6 factorial multiplied by 2 factorial. It's the same thing really. Just say 2 factorial times 6 factorial. And that gives us 3,600 ways. So that's 3,600 ways that they can be seated if Emily and Clara are not seated next to each other. Okay, and we move on to the final question in question 12. Okay, the final question says, the probability that a certain rugby team has all its players fit to play, okay, is 70%. So that the players are fit to play is 70%. Then the probability that they will win a game if their players are fit so that they will win if the players are fit is 90%. Then they tell us that when they are not fit, the probability of them winning becomes 45%. When they are not fit, the chance of them winning or that they win is 45%. And we need to calculate the probability of them winning their first game. Okay, this is one of those that you think about it, and let me actually just say it like this before actually saying what kind of diagram we're going to use to represent this. Do you see how they are working with this information? They tell us the probability, right, that they are fit to play is 70%, right? Then the probability that they will win if they were fit. So in this case, they were fit, right? And what is the probability that they will win if they were fit? So it means that they would have to be fit first before they would win. So this looks like something happening as a result of another thing happening before that. That is what we call dependent events. And we're going to see that in tree diagrams. So let me represent this as a tree diagram and then it will make more sense. So the first thing they tell us is that the probability that they are fit to play is 70%. So these are the rugby players. We have this. They're either fit to play, and that is 70%. And so the opposite of being fit would be not fit, right? So we'd say the probability that they are not fit would be the remaining 30%. Okay. And this is why I say it's dependent events, because something happened that caused another thing to happen. So they say the probability that they will win if all their players were fit or are fit is 90%. So the probability that they will win if they were fit. So it means now after we see that they are fit, they can either win or lose. So win or lose. We can represent it as a tree diagram. So fit and they win is 90%. So it means that the probability that they're going to lose if they were fit would be 10%. Okay, because that's the remaining part of 90. 90 plus 10 will give you the total 100%. And what else do they tell us? They tell us that when they are not fit, the probability of them winning becomes 45%. So when they are not fit, right, the probability of them winning becomes 45%. So when they are not fit, what is the probability of them losing? That would be 55%. That is the total that will give you 100. So this is what we have. And all in all, we just need to calculate the probability that they will win the first game. So what is the probability that they're going to win, given the information we have? So this is how we can look at this. We don't care regardless of whether they were fit or they were not fit. They just need to win. That's really all we're looking at. So this is what we're going to do. Okay, so whether they were fit or not fit, at the end of the day, we want them to win. So let's start with the fit. If they were fit, the probability that they win is over here. So we're going to take these probabilities and multiply them. So this is one of the probabilities that they will win. 70%, which is 70 over 100, multiplied by the 90%. Okay, so that's one probability that they win. Any other probability that they win, does that happen anywhere else? Yes, it does. When they are not fit, the probability that they will win is 45% here, right? So we have to actually take that as well. So that would be the 30 over 100 multiplied by the 45 over 100. So these two, right? These two probabilities we're going to get. We are going to do what with them? Because they are both probabilities that they win, regardless of whether the rugby players were fit or not fit. So we are going to add these two together because that would give us the total probability that they will win. So let's go ahead and just work out that calculation. So we would calculate it like this. Okay, so it's exactly the same thing, we're just adding it. And let's go ahead and find out what we get. Okay, so because our probabilities were represented as percentages, we can put our final answer as a percentage as well. So I'll just say it's equal to, and well, I'll say it's equal to, you could clear it and just say ons times 100. Okay, so that same answer multiplied by 100 so that it's in the form of a percentage. I will write it, of course, as a decimal first. So 0.765, which if we put in percentage format, is going to be 76.5%. This is the chance that the players would win regardless of whether they were fit or not fit. Okay, so that is the final answer, and that is the last question for this paper. Okay, so we're on question 10, and 10.1 says this. It says A and B are independent events. Okay, the probability of A is equal to 1 over 3 and the probability of B is equal to 3 over 4. You need to determine the probability of A and B. You need to remember what all of these things means. You know, they always mention this thing at first. They always say they're independent, or they would say things like they're mutually exclusive. You need to know what it actually means. If events are independent, what it means is that the probability of A and B would be found by finding the probability of A and multiplying it to the probability of B. That's what independent events mean, right? So since we know that now about independent event, we can use this to actually find what they're asking us for. They want us to find the probability of A and B. You see that this is the perfect equation for it. Okay, so to find the probability of A and B, we're going to use what they gave us as well. They told us the probability of A is 1 over 3. That's 1 over 3. Multiplied by the probability of B, which is 3 over 4. And if you multiply those two, you're going to get your answer. So that is 1 times 3, which is 3. 3 times 4, which is 12. 3 over 12. They have 3 as a common factor, so divide by 3. That's 1 over this. Divide by 3 is 4. 1 over 4. That is your answer. Okay, so that is the first question. Always take note of when they say these things, okay? Remember what independent events do. Remember what mutually exclusive events do. Remember, I do also have past paper videos. You can go there. Most of them, no, all of them, all the grade 12 videos have timestamps. I know that it's only 3 grade 11 videos I posted recently. I didn't put any timestamps because of the time. So you can always just skip to question 10 and actually watch the probability so that you can practice more and start understanding what they mean by certain things. Okay, moving on to the next question. Okay, so the next question says we need to find the probability of at least one event occurring. At least one event. This is another thing that you can check out my video on Venn diagrams. I'm going to link it. I will show you the actual video and probably link it in the description as well. And that really explains those things they speak about when they say probability of at least one and things like that. Okay, so I'm just going to explain this briefly. At least one of the events occurs. The only events they mentioned is A and B. That's all, right? In a Venn diagram, right? Because these are independent. When you're thinking about probability of at least one event occurring, let's look at it like this. Even if they intersected, right? We have A and B. If you're trying to find the probability of at least one event occurring, at least one just means at lowest one event must occur. So you need to take the probabilities of everything that has either one or more events occurring. The amount of events we have here is just 2, A and B, that's all, right? In this part, right, let me just highlight that like that. How many events are occurring in this region? It's only the probability of A, only, without the probability of B. So how many events are occurring here? That's one event. So we would take that. What about in the middle, the intersection? How many events are occurring here? That's 2 events because A and B are occurring here. So we'd also take that because we need to take at least one, meaning at lowest, one event must occur. You can take one, you can take two, as long as it's above one. And then here, how many events are occurring in the circle of B in this part without the intersection, of course? That would be 1 because the probability of B is occurring here. So do you see that we actually have to take everything here? Meaning this is the entire circle of A and B, everything here. This is really just finding the probability of everything. So probability of A or B. In other words, it's the probability of A union B. Everything. The combination of A and the combination of B. Everything. That's what we're finding. Okay? Just nothing outside the circle, of course. So that's what they're actually asking us for. They're asking us for the probability of A or B. So let's go ahead and find that. Well, all we have right now is the probability of A, we have the probability of B, and we have the probability of A and B. You can use the addition rule of probability of A or B. The addition rule states that probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And please check out my Venn diagram video. So I actually explain why we subtract that intersection. It's not because we are excluding the intersection, okay? You find out more about that in that video. So this is what we have. This is finally equal to, what's the probability of A? It is 1 over 3 plus the probability of B, 3 over 4 minus the intersection of A and B, that's A and B, 1 over 4 minus 1 over 4. And then we can just find that answer. You can go ahead and do this by yourself, but you can just use a calculator, which I will. Okay, and that answer is 5 over 6. And there we go. Okay, so that is it. 5 over 6 is the probability of A or B. That is the probability of at least one event occurs. Just to be a little accurate, what I would actually say is exactly what they said as well. Just so that it looks like, yeah, I actually am talking about this. So I would say probability of at least one event. Okay, so there we go. Now we can go ahead and move on to the next question. So we're done with that scenario. Okay, we have 10.2 now. So 10.2 says, the probability that it will snow on Drakensberg Mountains in June is 5%. Okay, then they say, when it snows on the mountains, the probability that the minimum temperature in central South Africa will drop below 0 degrees is 72%. Then they say, if it does not snow on the mountains, the probability that the minimum temperature in central South Africa will drop below 0 degrees is 35%. Okay, so first of all, notice that we're hearing a lot of this if this happens and if that happens. Okay, if it does not snow, right? That language is usually used in tree diagrams. This is probably a situation where we have dependent events because these events are being affected by previous events. So something happens and then it causes an effect on the next thing that is going to happen. Okay, so these are dependent events and we can already see, okay, this is going to be a tree diagram when you start reading the information. The first question is for us to represent the given information in a tree diagram. On a tree diagram, clearly indicate the probabilities associated with each branch. So just the probabilities associated with each branch, not the outcomes. Okay, so that's all we need to do. Let's break down this tree diagram. So they say the probability that it will snow on Drakensberg Mountain is 5%, of course, in June, right? So that it will snow. But then they said when it snows on the mountain, the probability that the minimum temperature in central South Africa will drop below 0 degrees is 72% when it snows. Okay, so this is clearly something that happens after it snows. So in the first branch, we have a situation where we're speaking about whether it's going to snow or not, right? So I'll call this snow, right? And then what is the probability that it's going to snow? They said the probability to snow on Drakensberg Mountain is 5%. As a fraction, that is 5 over 100. So the probability that it will snow is 5 over 100. So that means by default, the probability that it will not snow, let's say not snow, that would be what is left. 100 minus 5 is 95. 95%, right? So 95 over 100. I need a little more space for this tree diagram. Okay, so that's what we have first from that first statement, okay? When it's going to snow, it's 5%. Then they say, when it snows on the mountain, when it snows, the probability that the minimum temperature, so the minimum temperature will drop below 0 degrees is 72%. So this is at the snow column. We're saying if it snows, right, the probability that it's going to drop below 0. So we have another category now, below 0, right? The probability that it will drop below 0 is 72%. So that's 72 over 100. So if this category is below 0, what would be the category that is the opposite of this one? Okay, so it's either it's going to drop below 0 or it's going to be above 0. So we're just going to say, I'm going to call this one above 0. Technically above or equal to 0, because it could be 0 degrees as well, but I won't also just get too technical with that. Okay, so I just put it like that, above or equal to 0. Okay, so then that is going to be what? If we already know this one is 72%, when you add them together, they should give you a total. So what is left of this? So 100 minus 72, that is 28. So that's 28 over 100. That will be the probability that it's going to be above or equal to 0. Then here we have not snow. Let's just keep reading and see what we have. If it does not snow, right, on the mountains, the probability that the minimum temperature in central South Africa will drop below 0 is 35%. So this is in the column of it will not snow. The probability that it's going to drop below 0 again, below 0, that is going to be 35%. So 35 over 100. So what is the alternate one, okay, where it's going to be above or equal to 0? Honestly, I feel like they would just say above 0. I'm being too technical here. Okay, so 100 minus 35, that's going to be 65%. So 65 over 100. Okay, so that's what we have all through here. And that's all. Because they didn't say anything about multiply the branches. When they want you to find the branches being multiplied, then they will say, and also represent the outcomes of all the events being occurring together, really. Okay, they would say it in a more, put together way. So, but here they really just said, you have to draw it down and write down the probabilities associated with each branch. Okay, not really all of the outcomes, like combined. So that's all we need to do there. Next question, 10.2.2, they say, okay, calculate the probability that the temperature in central South Africa will not drop below 0 degrees Celsius in June 2024. So this is a prediction we're going to make based on the probability. But we need to be very careful as we do this. You see that they don't say that calculates the temperature, right? If it snows, that the temperature will not drop below 0 degrees. They don't tell you about whether it's going to snow or not snow. They only mention about it not dropping below 0. So we need to take everything that does not have below 0. Okay, everything that does not include the temperature dropping below 0. Okay, so here it drops below 0. We cannot take that one. Here it is above or equal to 0. We can't take that because this is not that case. Okay, it's not below 0. We need to take the case where it is not below 0. So we're going to have to take this, and we're also going to have to take this one because this one is also not below 0. But do you see now these are independent events? You cannot just take the events and then add it up together. They are happening together. Okay, it's either snowing or it's not snowing. Then it's going to drop above. It's going to be above 0 or below 0. That's how it's working. So you need to also, along with this, you're going to also take the branch that happened before it. So we need to take the probability that it's going to snow, right? And the temperature drops above 0 degrees. Okay, that's the first part we're taking. We're taking that. We're going to take the probability of it's snowing and the temperature is going to be above 0. I'm just going to call that above 0, right? And then, is that the only one we're going to take? No, we're also going to take this because here it's also above 0 degrees as well. But the branch that was attached to this, right, the thing that happened before it was this. It did not snow. So we need to take the probability that it's not going to snow as well. So we're taking that probability that it's going to not snow, and the temperature is also going to be above 0. That's what we're taking. Now, what are we doing with these? Well, if you look at it in a language sense, what they asked you when they told you to find out the probability that the temperature will not drop below 0 degrees is you need to take everything that does not have below 0, right? So what we're saying is that means we can take the probability that it will snow and the temperature will be above 0, or we can take the probability that it's going to not snow and the temperature is going to be above 0. So what does this word or mean? In probability, or means to add. Again, if you watch the Venn diagram video, you will see why all these things mean those specific things, okay? Or means to add, and I do explain it there as well. So what we're going to do is take that probability and add it to this probability. So the probability that it will snow and be above 0 is what? Well, you're going to have to multiply them because that's how we find the total probability of these two events happening at the same time. So that is the 5 over 100, right? Multiplied by this. So we're going to take the branches and multiply like this. The probability that it's going to snow and it's going to be above 0. That's 28 over 100. Let me write this bigger. 5 over 100 times 28 over 100, right? We're going to take that. And because we have or, it means to add. So we're adding that to the probability that it will not snow. Probability that it will not snow is 95%, right? Multiplied by, so probability that it will not snow and be above 0 degrees, which is 65. So 65 over 100. And we'll get our answer like this. Okay. So really, we're just adding these two together. Okay, in an exam setting, I'll probably write this a little neater. And I get an answer of 1,263 over 2,000. And I like to leave things like that. I don't actually like writing things as decimals because I feel like some parts of it is cut away. Like this, I can get the percentage even. Like it just feels more put together. Okay, so that is the answer. You can leave your answer as a percentage, as a decimal, as a fraction. It's still fine because it's probability. We're done with 10.2. Now we move on to 10.3, which is the last question. And okay, let's go. So 10.3. In 10.3, you see that they say 10 learners stand randomly in a line, one behind the other. Okay, so 10 learners. Now, I like to visualize what's going on. So I'm just going to put 10 learners, right, standing in a line. Okay, so there's our 10 learners. And they say the first question is 10.3.1. 10.3.1 is asking, in how many different ways can the 10 learners stand in the line? Okay, so how we calculate that is like this. You're going to look at it like this. The first learner, when they have to stand in a line, they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 choices, okay, that they can stand in. They can stand in either the first, second, all the way to the 10th position. So that learner has 10 choices. Then after the first learner is standing, then the second learner has how many positions to stand at? 9 more positions, right? The third learner will have 8 more positions. 4th, 7th, 5th, 6th, 5 more positions, 4 more positions, 3 more, 2 more, and 1 more. And all of this on the calculator is called 10 factorial. So 10 factorial, you can just go ahead and find out what that is on the calculator. 10 factorial, you just press shift and then that button with the extra power of -1. And we get, so 1, 2, 3. Okay, so 3,628,800 ways. These are the different arrangements that they can stand in. Okay, that one was okay. It was good. It's quite simple. The next question, 10.3.2. Okay, so for this last question, I just decided to expand the page because it's really the last question. I'm not really going to need the question paper anymore. So the last question says, calculate the probability that there will be 5 learners between the 2 youngest learners in the line. So you have the 10 learners standing, right? And the question wants us to calculate the probability. So let me also just remember they are asking for probability that there will be 5 learners. So 5 learners between the 2 youngest learner in the line. So we have 2 youngest learners and we need to calculate the probability that there's going to be 5 learners in between them. So let's think about that. If the 2 youngest learners, let's just say a first scenario can be like this. So let's say this is one of the youngest learner and then there's supposed to be 5 learners in between them. So 1, 2, 3, 4, 5. Then this would be the second youngest again. Okay. So if we're thinking about this, let's also just give them names. I thought about giving them names, like actual names, but I feel like that's going to get confusing. So I'm going to just call them youngest learner 1 and youngest learner 2, right? So let's look at how this can work. We have to find the amount of ways that they can be seated, but there needs to be 5 learners in between the both of them. Okay, so how do we make sure that this youngest learner, they're always going to be in between the 5 learners, not the 5 learners, but just 5 learners. Okay, they didn't specifically say that these are 5 particular learners. So let's think about all the ways they can stand. Well, the first way of them, they could stand like this. Okay. And a second situation is where the youngest learner can be standing here, for example, right? That can be the youngest learner. And then that's the youngest learner again. Either ways, in this placement, we can still see that there are still 5 learners in between the both of them, the 2 of them, right? Still 5 learners here. So they can either be standing in the first, and let me actually write that, the first and the 7th position, or they could be standing in the 2nd and the 8th position. Let's also keep seeing the other ways that they can stand. Or they could be standing in the 3rd and the 9th position, and in the 4th and the 10th position. These are all the ways that they can be standing, and 5 learners will always be in between them. Okay. But I also have to think about the fact that these learners, right? The first learner, the first youngest learner, doesn't necessarily have to be standing here. The first learner can actually be standing here. So they can actually switch places because technically there's still going to be 5 learners between them. So we can also have situations like that as well. Okay, I'm going to really just think about this question first. Okay, I thought about this question for a while and it was not making, well, the question makes sense. I understand the question, but getting to that answer. So the thing about it is, we're looking at this and we know, yes, the first learner, the first youngest learner and the second youngest learner, they can switch places, right? They don't always have to stand in these 2 positions. So if you look at the amount of ways that the 2 youngest learners can stand, there are actually 2 ways that they can stand. They can either stand as learner, first youngest learner and second youngest learner, or second youngest learner and then first youngest learner. So from them, I'm seeing that, okay, that's 2 ways that they can stand. 2 ways, which I usually like to call 2 factorial, right? But now I have to think about this 5 learners in between. I've thought about the fact that, okay, there are 5 learners in between. So why don't I just say, okay, 5 learners have to be in between them. So I can say 5 factorial. But the thing about this, and the reason I kept thinking about this and saying, I don't think I can actually do this, is because when you say 5 factorial, what you're doing is you're creating a group. So you're saying that these particular 5 learners have to be standing, okay, in between the 2 learners. Now, the thing about that is that may seem correct. That may seem like, yes, that's true. They're supposed to be standing there. But this question doesn't give any indication that there has to be these particular 5 learners standing in between the 2 youngest learners. That's the issue that I'm seeing here. It wasn't specific about that. You see, they didn't say, they said calculate the probability that there will be 5 learners, not that there will be 5 specific learners, right? Like 5 particular learners. Only these 5 learners can be standing in between them. It doesn't say that. So with that being said, it means that, for example, this learner could be one of the 5 learners here as well. And this learner could also be one of the 5 learners here. And that's the reason I keep on not wanting to say 5 factorial, because 5 factorial means you're creating a group. You're saying these 5 particular learners must stand in between the first and the second youngest learner. So, okay, this is the conclusion I'm coming to. What I'm going to do here is find out the possible ways that we can actually have this particular arrangement first. This arrangement can be viewed as like this, basically. We can look at it as the first and the 7th learner is going to be the 2 youngest, or 2nd and 8th, and so on, right? But then remember that these 2 youngest learners, they're not the same people. They're 2 different people. So we can also have situations where the youngest learner, the 2nd youngest learner is first, and then the 1st youngest learner is 2nd, right? So I'm also going to put those probabilities as well. So it's going to be exactly this, but just having y2 and then y1. Okay, so I know it looks a bit crazy, but this is what I'm thinking of now. So looking at the positions, the possible positions that they can be standing in, this would be everything, right? They can either be in the 1st and 7th position as y1 and then y2, or as y2 and then y1, right? And the 2nd and the 8th, and of course we can see the orders of them. So you see that there's 8 possible categories that we can have, right? 8 sort of arrangements. This is not obviously the final answer. 8 sort of structures that they can be standing in. But now we also have to look into each of these. So if I could find the amount of ways for each of these, I could just add them up together and then find the final answer. I know it's a messy way, but I'm really just trying to unpack everything, really. Okay, so in this first arrangement, right, I'm looking at the 2 youngest learners, they're standing like this. I don't have to say, oh, there are 2 ways now that they can be standing like this anymore. The reason why is because I already have that second situation here, which I will calculate separately. Okay, so since these 2 learners are already standing like this, what are the possible ways that everybody else can be standing if 5 learners have to be in between the 2 youngest learners? Now, considering the fact that it's not 5 specific learners, right? Like 5 particular learners like Tandy, Bob, Josh, and 2 other learners have to be standing in between the 2 youngest. It's not 5 particular learners. It's just 5 random learners. So for example, this learner could be in here as well, part of the 5 learners. Okay. And then that maybe one of them could be there. So that's the thing I'm thinking of. And that's why I don't want to group them. I feel like grouping them is a dangerous thing now, because now I'm creating this group and saying that these particular 5 learners must be standing here. And it doesn't seem like what they're asking for. They're saying just that there will be 5 learners between the 2 youngest in the line. So by that logic, we have to look at it like this. These are 8 individual learners. They can be standing as, for example, this learner can be here, for example, and then this learner there, right? Since they have the freedom to move around like that, but there has to be 5 learners in between, right? I'm still going to have to look at it like this. After the 2 learners are standing in their positions, 2 youngest learners are standing, how many more positions are there for a learner to stand in? There would be 8 more positions. So for example, this learner could either stand here, that's 2, 3, 4, 5, 6, 7, and 8. 8 places that this learner would have a choice to stand at or stand in. So that learner will have 8 choices. Then after that learner is standing, then the next learner would have how many more places that they can stand at? 7 places. And then 6 places. And so 5, 4, 3, 2, 1, which is really 8 factorial, right? Because I'm really trying not to group them. If I group them, I'm saying that these 5 particular learners must be standing here. So I'm taking out the arrangements individually and actually going to calculate it, they'll probably look the same though. The way I'm thinking about it, it really feels like it's going to all look the same. Because the thing about counting principles, right? They only tell you the information. They don't show you how it looks. You can find out, for example, right? Maybe there's even like a 5 out of 98 chance that these two learners can be standing between 5 learners. But the counting principles will not show you how they're standing. They're just going to count the amount of ways they can be standing in that order and then just give you the number. So I'm actually representing it out like this. I'm trying to think about all the possible ways and represent that, then calculate it individually. So this is one category that we're looking at. And I'm saying that these two learners have to be standing like this. And the 8 learners get to move around really. Like this learner, for example, doesn't have to particularly be here. This learner could be there. And then this learner could be here, right? And so that's why I'm still saying 8 factorial there. If you look at this second case here, it would be the same thing. These two learners have to stand here. Then the rest of the learners would have how many positions to stand at? 8 positions. So this one, for example, would get to stand here, 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 or here. That's 8 positions. Then after that one is standing, this one gets to stand either here, 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 all the way to basically 7 positions, and then 6 positions, and then 5. That will also be 8 factorial ways that they can stand. Okay, given that these two learners are standing here. And then this one, same thing. These two learners are here. That will also be 8 factorial ways. 8 factorial, right? For these 8 categories, they're going to be 8 factorial. So if you look at what's going on, what we're doing is we're adding 8 factorial 8 times. That's what it seems like we're doing. Adding 8 factorial 8 times. So that would be 1, 2, 3, 4, 5, 6, 7, 8, right? In other words, you can decide to add 8 factorial 8 times, or you could have just said 8 factorial times 8. Okay, so 8 factorial times 8 is going to be 8 factorial multiplied by 8, and that is 322,560 ways, right? But also do remember that they did say you need to find the probability. So you see, I'm trying to find the categories out by hand. Then we have to put this as a probability, right? So it's going to be this, right? In other words, 8 factorial times 8 over the total number of ways that they can stand, okay, if they were not being grouped or manipulated in any way. And we know that total number of ways was 10 factorial, the 10 learners, right? So over 10 factorial. And then I'll just simplify that. And this gives me 4 over 45, which I think it can be simplified to, you can leave it as a decimal as well. I think that's recurring. Yeah, it's recurring. So 0.89 as a decimal, but I actually do like leaving it as a fraction. So that would be my answer there. But yeah, we'll see when the memo comes out. Okay, so we're on question 11, and question 11.1 says 2 events A and B are such that the probability of A is equal to 0.4, probability of A or B is equal to 0.52, and then A and B are mutually exclusive. And now we have to calculate the probability of B. Okay, so to find this, we need to understand what they mean by the probability of, or A and B are mutually exclusive. So if things are mutually exclusive, okay, you can see it like this. I usually just say this to my students so that they'll remember. The events have mutually decided to exclude each other. Okay, so mutually exclusive events are events that do not intersect. Okay, so that will be event A and B. So because they are mutually exclusive, as you can see, they do not intersect. So they don't have an intersection. And I want you to note that when they say events are mutually exclusive, that's really what they're trying to point out. They're trying to tell you that they don't intersect. So what does that actually mean in probability? If things do not intersect, what it means is the probability of, so we're talking about A and B here. So the probability of A and B, because they don't intersect, okay, there is no probability of A and B. There is no event where these two events are happening together. So that would be equal to 0. So we can use this now to actually find the value of the probability of B. So we'll simply use what they told us here. They told us the probability of A or B. Now that has a formula. The formula for that is the probability of A or B is equal to the probability of A plus the probability of B, and then you usually say minus the intersection, right? Minus probability of A and B. But we already know that's 0, so we don't even have to include it because it's like minus 0. So let's fill in what we have and you'll see we'll find the probability of B. So probability of A or B, they told us that that was 0.52. And this is equal to the probability of A, which is 0.4, plus the probability of B, which is what we are looking for. And now you see that we have formed an equation. We can leave the probability of B on one side and say 0.52 and take the 0.4 over. This is kind of like 0.40. So it's like 52 minus 40, which will give you 0.12. And that would be your probability of B. Okay, moving on to the next question. The next question, 11.2, says, the items that a learner bought at the tuck shop were recorded over a period of time. The probabilities of the learner buying a sandwich, a chocolate, and a juice, so those are represented by those letters, are shown in the Venn diagram below. So this is the Venn diagram that we have, and everything is in decimals. That is not a bad thing, okay? Decimals are already in they're already in probabilities, okay? So because they're already in probabilities, you don't have to think about, oh, what do I have to put it over? It's already in a probability format. So we have 11.2.1. What is the probability that the learner will buy a sandwich? Okay, so if you guys want to learn more about Venn diagrams and you want to do better with Venn diagrams, I'm going to recommend these 2 videos that I'm showing you now on screen for you to go ahead and practice with. So you can go ahead and check that video out. I hope it really helps. So they want the probability that the learner will buy a sandwich. So you see that we have the different circles, the chocolate, juice, and sandwich. You see, they did not say the learner is going to buy a sandwich and not a chocolate and not a juice. They just said a sandwich. So regardless of whether the learner is going to buy a chocolate or juice, as long as they bought a sandwich, we're going to take that. So that would be, when you're looking for a sandwich, it will be the entire circle of sandwich. Because every probability here includes whether the learner bought a sandwich, okay? Here the learner bought a sandwich and a chocolate, but they bought a sandwich, okay? So that's what we're going to take. We're going to add all of those numbers up, and that should give us our answer. Okay, so this is what we have. The probability that the learner bought a sandwich would be 0.16. And that will be our answer for that question. Okay, moving on to the next question. Okay, 11.2.2 says, calculate the probability that the learner will buy at least 2 of the 3 items. So calculate the probability that the learner will buy at least 2 of these items. I also explained this in that video of Venn diagrams in the first video. So let's actually look at it like this. We want to see the probability that the learner buys at least 2 items out of all the items that we have here. Just go to each probability and ask yourself, in that part, in that 0.04, that is just the chance that the learner will buy a chocolate, right? How many items did the learner buy here? They bought only 1. They may not have bought 1 chocolate, okay? But they bought 1 item type, which is the chocolate. Because this circle, right, in the circle, as you can see, it is not inside. It is not included in the sandwich. So it's not like this situation where the child is buying a chocolate and a sandwich. This is just a chocolate on its own. So it means here the child bought 1 item. We can't take that. They said at least 2 items. So also just note that at least means at lowest. So it means that the lowest amount of items that this child must buy should be 2 items. So as long as it is 2 items and more, then we're going to take that. Okay, so we can look at each of it and ask, so how many did they buy here? 1 item, only a chocolate. Okay, how many items did the child buy here? That would be 2 items because the child bought a chocolate and a sandwich. You see that is part of the intersection of chocolate and sandwich. Okay, so that's going to be included in our calculation. What about this one? How many items did a child buy here? That's 1 item because you see that's only sandwich. There's no intersection here. They bought 1 item. What about here? That's 2 items. That's intersection of chocolate and juice. Okay, so that will be 2 items. And here, how many items is that here? Well, as you can see, that's the middle. That's the intersection of chocolate, sandwich, and juice. So that's 3 items. This child must buy 2 or more because they said at least 2 items, meaning at lowest 2 items. So 2 or more items is fine. So we include that as well. And lastly, this one, because this is juice and sandwich. Okay, so these would be the answers that you would add up. That's what you're going to add up to find out what is the probability really that the learner is going to buy at least 2 items. And when we add these all up together, we get 0.01, which is really a 0.10. But when the calculator simplifies it, it's 0.1. Okay, so 0.1 actually. Okay, so that's what we get there. And that is that answer. Moving on to the next question. Then we're on the last question in this Venn diagram, and 11.2.3 says, calculate the probability that the learner would not buy any of the 3 items. So the only items we have are the 3 items. So if we're finding the probability that the learner will not buy any of the 3 items, we will be finding the probability that is outside the circles. Okay, because this would be people who didn't buy any of these. So how do we actually find them? Well, you have to think about it like this. Each of these probabilities, when you add them up together, they will give you the probabilities of all the items that were bought, right? Of all the 3 items. So if you want to find the probability that the learner did not buy any of these items, you're going to have to think about what everything, including the one outside, right, is going to give you. What everything is going to give. What's the probability of all the items and even the probability that the learner is not going to buy any of the items? When you add all of these up together, because they're already in decimals, it means they're already been written as a probability. Okay, the probability of every single thing added up together is 100%. As a decimal, you can say that is 1. So we're going to have to say 1 minus the probability that the learner is going to buy every item that they bought. And that will be minus everything we have in all the circles. So we'll take 1 minus everything because it's in decimals, and it's going to give us the probability of the learner not buying any of the items. So that is going to look like this. Also, the notation doesn't really matter that much, but I'm really just saying it's the probability of not A or not B or not C. If you watch the Venn diagram video, you understand what the word or means better. In a nutshell, really just means to add. Okay, so when we calculate this, it's 1 minus the addition of everything in the circle. So this would be equal to, when we finally calculate that, we get 0.57. So 0.57, which is really a 57% chance. Okay, so it's really higher than every other item that he has bought. Okay, so that is it for the Venn diagram question. And then we move on to 11.3. Okay, so now we're on question 11.3, and it says 7 guitar players, each with a different name, participate in a concert. In how many different ways can the names of the guitar players be listed one below the other in the program? Okay, well, they said there were 7 guitar players, okay, with different names. So how many different, well, that doesn't really apply to this, but how many different ways can the names be listed one below the other in the program? So if we're looking at it like the list, there's 7 places because there's 7 guitar players, right? So that's 4, 5, 6, and 7. So since there's 7 guitar players, when you're thinking about where the first guitar player is going to be seated, that guitar player has 7 choices, okay, to sit at. You can sit here or here or here or here or here or here, right? So that person has 7 choices. Then after that person is seated, because they say one below the other, which is probably just their hint for no repetition. So after that one is seated, the next guitar player has how many places that they can be positioned in. That's going to be 6 places left because the first one is seated. And then the third one will have 5 places, and 4 and 3 and 2 and 1. And to find the amount of ways, we would multiply all of these. So as you can see, that is actually 7 factorial. And if you find 7 factorial on your calculator, I think it's like 50, 40, let me see. So 7 factorial, yes, it is 5,040 ways. Okay, so there we go. So that's the first question. Moving on to the next question. Then 11.3.2 says, after the performance, the guitar players wait backstage. There is a bench with only room for 4 to sit on. Okay, so the 7 guitar players are waiting backstage. And then there's this room that has a bench for only 4 people to sit on. Okay, so the question is, what will be the probability that the 4 guitar players will be sitting in alphabetical order from left to right? Okay, so let's look at this. The guitar players, there's 7 of them, right? They want the probability that 4 of them are going to be seated in alphabetical order. Well, if they're in alphabetical order, there can only be one way for that to actually happen, because you're either in alphabetical order or you're not in alphabetical order. Okay, just knowing that, because they did mention that their names, they have different names, right? So as long as there's no guitar players with the same names, then if they're seated in alphabetical order, then of course we should have only one way that can happen. Okay, since it's the probability, we know that it is 1, right? But it's over something. They gave us a scenario here. So the scenario is that we still have the 7 guitar players waiting backstage, but then there's this bench with only room for 4 to sit on. So this would be what it's out of, because this is what we're comparing it to, really. They're saying now that these 7 guitar players are sitting backstage, there is a bench with only 4 places for them to sit in. Now, from that scenario, what is the probability that they will be seated in alphabetical order? So we're going to have to find out how many ways can these 4 guitar players be sitting on that bench. Well, let's remember that there are 7 guitar players originally. Okay, so let's just give them names. Instead of giving them names, let's actually just name them in letters. The reason why is because they should be in alphabetical order, right? So I think this would be easier if we use letters. So if we go, let's say the first one is A, B, C, D, E, F, and G, right? So these are the 7. Now there are only 4 places to sit at. Let's think about it like this. So let's think about the first place. What are the choices that we have for the first place? Well, the choices that we have is that we have 7 different guitar players. Now, any one of them could be seated in this first place. So it means that there are literally 7 different choices of guitar players that could be seated in this first place. So that's 7 choices that we have there. Then, after that first person is seated, how many choices do we have? Like, who could be seated here? Since the first one is already seated, you'd only have 6 choices of guitar players who could sit here. So it's like, let's say we said A was seated in that first place. Then it means that there are only 6 more guitar players, right, that could take this second position. Then after that one is seated, let's say it was B, right, there would only be 5 more positions and then 4 more positions, okay? So that's how we're going to get the total amount of ways that they can be seated on the bench, right? Just on that bench. So that would be, we'll have to multiply that, of course. But then they say, what is the probability that the 4 guitar players will be sitting in alphabetical order from left to right? The only way they can sit in alphabetical order is one way. Because even if it was just B and D and let's say E and G, if I decide to move G here, they're not in alphabetical order. Okay, so regardless of who is sitting, there's only one way they can be in alphabetical order. Okay, so that means to find the probability, we will just say 1 over the scenario they gave us, okay, which is just all of this. If we multiply that, so let's see what that gives us. 7 times 6 times 5 times 4, it is 840. So the probability is 1 over 840. Okay, so that's the answer there. And then moving on to the next question. Okay, so we are on the last question, 11.3.3, and it says, during the performance, the 7 guitar players sit in a line on stage. 4 guitar players are female. Okay, so let's highlight that. 4 guitar players are female and 3 are male. Then they say, in how many different ways can they be seated if the males may not sit next to each other? Okay, so the males may not sit next to each other. Honestly speaking, when I'm thinking about this, because they told us that 4 are female and then 3 are male. When they say in how many different ways can they be seated if the males may not sit next to each other, I'm kind of thinking, do they mean like the 3 males specifically must not be next to each other like that? Or do they mean like we must just never have any males next to each other? Okay, let me just think about that. Okay, I'm just going to go with this. The thing is, they're saying if the males may not sit next to each other, okay? So since they cannot sit next to each other, I'm going to see it as no males must be sitting next to each other. Okay, not necessarily just the 3 males sitting next to each other. Okay, so even if we have 2 males sitting next to each other, I mean, that would be a situation where you have males sitting next to each other. So since they said no males must be sitting next to each other, then we should also not have situations like this. Okay, so this seems like, in fact, it looks a lot similar to last year's November paper. You'd have noticed that in November 2023, the paper 1, the probability part, which I did post the video on, that last question was also one of those types where if you think about it as a picture, you'd be able to sort of think your way through that question. Okay, so you had to kind of like visualize what was going on there. This one also seems like one of those, so there's going to be a lot of writing. Let's just think this through. So we need to put this scenario where no males must be seated next to each other. Okay, fine. So let's think about the places we need to put the males so that they're not next to each other. How about we put down the females first? So we're going to put it as female, 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 and female. Okay, so we know there are 3 males. How should we place the males so that there are no males next to each other? The only places to place them, I see 5 places that we could put them. We could put them here. You could put a male there. You can put them here, 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 and here. Okay, so if they're in between the females like that, in any of these 5 places, then they're not going to be, next to another male. Okay, so the males can be seated in these 5 places, but remember that there are only 3 males. So we'd have to kind of try to think about the arrangements that can be made if the males are seated in any of these 5 places. Okay, so the first one, okay, and I'm also just going to copy this just so that I can constantly just paste it down and then think about the placement of the males. So when we're looking at this, the first type of placement I can think of is where I put a male here, a male here, and a male here, right? So there. Then secondly, the second way the males can be placed would be maybe you put a male here, a male in the second place, and then we can move that male there. And then in the third one, we'll move that male there. Okay, so male here, then we put this male over here. Then of course in the third placement, we can have a male here, a male here, and then we're going to move that male right to the end. Okay, so that's not all the types of placement. I guess we have to categorize this. We can actually call this, let's actually focus on this being the placements where we make sure that the male is first. We have a male in front of the female, right? So I'm going to call that male first. Okay, then we'll also deal with situations where the male is second, okay, instead of first. So what other placements can we have? We can also place it like this. I can also see other ways that the males can still be first. So a male is first. Then instead of putting this male second, I can put the male third and then another male. Then in the second one after this, we can have still male here, male in the third place, and then this male can be there, okay? So like male, male, and male, like that. Okay, we could have that as well. And then there's one more way we can put this. So how about we put, again, the male first. I'm looking at all the situations where the male is first, right? So a male here, and then, so you see that here we were working with the male being first and then a male being second. You know what I mean by second, like in the third position, right? So it's the second male here. And then we also worked with a male being first and then a male being third. Then we can also work with a male being first and then a male being fourth. That makes sense. And male. But you see that after this, if you try to, try to push this male to that side. So if you try to push that male, so if you had like a male first, then you had male, male, then you see it's not going to work out here anymore because now the males are next to each other. So that will be the end of when we try putting a male first. Okay, so how many? That's 1, 2, 3, 4, 5, 6 arrangements so long. Okay. Now remember, there's still 5 places. There's 5 places that the males can stand. So we can actually now try where the male is just second. Okay, so we keep this aside and then we try male second. Okay, so I couldn't really move that nicely, so I'll just leave it in the middle there. So let's try when the male is second. Okay, so in this placement, when we have our females, we're going to put the male second. Okay, so if a male is second, we could have a placement like male, male, and male. Okay, then again, if the male is second, we can try like male, and then let's keep that here and then move that one to the end, male. And then again, this is very tedious, but I feel like it's the only way that personally I can visualize what's going on. So the other one that we can have, well, we can't push this male any further. So now we can try still leaving the male second, but instead the second male is not going to be here anymore. Let's put the second male here. So male like that and male, right? And then you see after this, you can't really move this male here because then it's going to be next to another male. So that would be the only placements for the male being second. Okay, let's try placements where the male is third. So male third. So male third. Let's try that. Okay, we're going to have as our females again. And let's try putting the male in the third position. You see what I mean by the third position, the third male position that we have, since we have 5 different male positions. So the third one, that will be male, male, male. I don't think you can go further than that though, because like male, 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 that's it. You can't move that male there, because he'll be next to the other male. So this would be all the possible ways that they can stand and the males will not be next to each other. These are all the possible ways. How many arrangements is that in total? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we have 10 arrangements, 10 ways that can, it's not 10 ways in total. It's 10 arrangements, 10 picture arrangements. That's what I'll just call it. Okay. So now that we have that, we also have to consider what's going on in each arrangement. Remember that these females are not the same people and the males are not the same people either. So it means that this female particularly doesn't have to be seated here. She could be here or here or here, right? Because of that, we also have to now consider what's going to happen with that, the kind of pattern it's going to create. So let me just move this here. So looking at the pattern that is being formed, we're really just, it's like you're grouping the females. Just looking at it in this picture, it's like you're grouping the females, but in a pattern way. You're saying that a female must be in the second position, in the fourth position, in the sixth, and in the seventh position. This is a group. So those females, because they're not the same people, they're different people. This female doesn't have to be here. She could be here, here, or here, right? And so when she's seated, the other female doesn't necessarily have to be in this position. She could be here, here, or here. So she has 3 places. And then this one has 2 places. And then she will have 1 more place. Because of that, the females make a group of 4 factorial, right? Then we can also do the same for the males. So we'll say multiply by, and let's look at the males. The males as well, they've also been put in a pattern, in a group, okay, group-like pattern. So a male must be first, a male must be third, and a male must be fifth. Because of that, we can also go ahead and say that that's going to be 3 factorial. For the same reason, this male doesn't necessarily have to be in this first place. He could be in the 3rd place or the 5th place. And after he's seated, the second male doesn't have to be in this 3rd place. He can be in this 3rd place or the 5th place. And then the last male would only have that place. So that's why it's 3 factorial again. So that's what that group creates. And then if you do the same for every other group, you see that it creates the same thing. Because all we're doing is we're saying that the females have to be in these particular positions and the males have to be in those particular positions. So that will be also 4 factorial times 3 factorial. And we'll keep on having the same thing, 4 factorial times 3 factorial. But how many times are we going to have this rule? See, same thing, 4 factorial, the 3 males again, 3 factorial. We're just grouping them in that way. So that's the thing about the counting principles. The number, the answer that you get is not going to show you how they're seated. It's just going to count it. So when we actually find in it, when we represent it as a picture, then we can actually see how they're seated. Okay, so because of that, what I'm going to say is, since I know that there are 10 pictures or 10 categories that we can have like that, I'm saying it's 10 of that multiplied by each of them are going to all be 4 factorial times 3 factorial because of the type of patterns they create throughout. So 10 multiplied by 4 factorial times 3 factorial. And that's going to be our answer. So let's go ahead and calculate that. Okay, and the answer that I get there is 1,440 ways that they can be seated. Okay, so I think it was a lot similar to the November papers one as well, because they also had something like that where you kind of had to represent it and see the different patterns that they create. We are on question 11. So finally, the probability section of this paper. And question 11 says, a certain number of learners are sitting for examinations in mathematics, tourism, and geography. All these learners, okay, so this is a Venn diagram. They're just giving us info about everything. So I do have a video on Venn diagrams where I really explain how Venn diagrams work in detail. So you can check these 2 videos out, okay, part 1 and part 2. Please start with part 1 because it really just gives a breakdown on how they work. And then in part 2, we actually deal with an activity. Okay, so you can check those videos out. They will really help you to understand these sections. Okay, so you see with Venn diagrams, the first thing you need to start with, okay, is the intersections. But I'm going to just still read it so I can see the kind of intersections that's going on, and so that we will know what the Venn diagram should look like, okay, where they intersect and things like that. So first of all, they tell us that all these learners sit for at least one of these exams. Very important. Every single person is sitting for an exam. So that means you do not have people who are not sitting for an exam. You will not have people on the outside of your circles. Okay, that's all that means. Then they say the total number of learners who sit for mathematics is 22. Now that number, I won't even touch it yet because it's telling you the total people who sat for maths, meaning that's the entire circle of maths. Okay, so it's usually a rectangle. So that's an entire circle of mathematics. I don't have to write that down yet. You have to actually start with the intersections. That's how Venn diagrams work. And then the total number of people sitting for tourism, same situation. This is everybody sitting for tourism, regardless of whether they are sitting for other subjects. Okay, as long as they sit for tourism, this is everybody, 16 people. Okay, so 16 learners there. Then the total number of learners sitting for geography is 18. Same case, okay, that's the total number. Then they start saying 5 learners sit for mathematics and tourism, but not geography. So that means these learners are sitting for, they're going to write mathematics and tourism only, okay, not including geography. So that will work like this. If you have mathematics, and I actually just want to put them in their order, maths, tourism, and then geography. So we'll still see, of course, if they actually do intersect and where we can actually see that. So maths, tourism, and geography. If they tell you that 5 learners sit for mathematics and tourism, but not geography, this means this is the intersection of maths and tourism, excluding anything related to geography. So that will be this circle, this little part over here. See how I didn't include this part? Because this part includes geography, and I don't want to include geography. So that's really what they're saying there. They say 4 learners sit for mathematics and geography, but not tourism. So maths and geography, but not tourism. So that will be this little section there. And then, so like this already, you can see everything does intersect, seeing that they have little intersections of 2 circles. So we have 3 learners sit for tourism and geography, but not mathematics. So tourism and geography, not including anything related to mathematics. So that's what we have there. And then they tell us that 6 learners sit for only tourism. Okay, so we have to draw a Venn diagram. Let's actually start drawing the Venn diagram now that we know that they actually do all intersect. So we have our circle for mathematics and then tourism and geography. Okay, so with these, we always start with the intersections. That's what you should always do. Now we already know there is nobody on the outside because they already told us that all the learners sit for at least one of the examinations. So there's nobody who is not sitting for an exam. Okay, makes sense. If not, you wouldn't be in the exam hall. So now let's start with the intersections. That's where you have to start. 5 learners sit for mathematics and tourism, but not geography. Remember where that goes? Maths and tourism, but not geography, not including geography. So that is 5 learners in total here. And then 4 learners sit for mathematics and geography, but not tourism. Maths and geography, not tourism. Then 3 learners sit for tourism and geography, but not mathematics. 3 learners, tourism, geography, excluding anything related to mathematics. Okay, so that's how that works. And now you see that we don't have the middle. Now, I can't just say we don't have the intersection of all and I'll just call it X. I can't really do that yet. I have to look into the details and see whether that is true or not. So you guys can actually mark with a pencil when you're done. So you know you're done with those ones. And now we're going to focus on the ones that we haven't touched yet. Now, we would like to, it would be nice to go to these bigger ones, but you see that we still have things missing here. This is missing and we need something to help us find it. So let's look at this. They say that 6 learners sit for only tourism. 6 learners are sitting for only tourism. What that means is that would be the learners here. Do you see that if you have a specific number here, this is excluding anything in any of the circles. It's just this part. So that is the 6 learners sitting for only tourism. 6 learners over there. And then you see that now we can actually find this intersection. All we would need is for them to tell us how many people are sitting in total for tourism, and we'll be able to know what exactly the intersection is. Do they give us that information? Yes, they do give us that information. So I'm taking this off because we're done. Do you see they do tell you about tourism? They say the total number of learners sitting for tourism is 16. So now we will find out exactly what is here. So them saying everybody sitting for tourism add up to 16. That is this entire circle. Everything here must add up to 16. So we can use this to find the middle. So if you saw the middle as X, we're saying that everybody here must add up to 16. So X plus 5 plus 6 plus 3 must give you 16. Okay, so let's go ahead and calculate that. So these two give you 11. 11 plus 3 is 14. So that's X plus 14 gives you 16. And therefore, if you take 14 over, that's 16 minus 14. So X is equal to 2. So there, your intersection is 2. And now we know that everything actually is complete. Let's fill in the remaining parts. So we're done with that tourism. Then they told us that the total number of learners who sit for mathematics is 22. Again, total for maths is 22. So everybody here must add up to 22. So to find out the people who are sitting for maths only, who are only going to write maths and nothing else, we would take the 22 learners, subtract by the 5 and by the 2 and by the 4, so that we can only find out the people who are here. Okay, that's maths only. Okay, so let's see what that would give. Together, these give -6, and then like that is -11. So that's 22 minus 11, which is 11. You can just do these calculations on your calculator. So only 11 learners sit for maths only, okay? Just maths alone. And then we have geography. So we're done with that. Then they tell us that the total number of learners sitting for geography is 18. Same thing. Everybody here must add up to 18. So we're going to take total of 18 and subtract by everything else to find out people sitting for geography only. So -4, -2, -3. So that's going to be, that is 6 together, -6, and that's -9. So that's 18 minus 9, which is 9. Okay, so only 9 learners are sitting for, so 9 learners are sitting for geography only. There we go. Our Venn diagram is complete. Moving on to the next question. 11.2, calculate the probability that a learner chosen at random will sit for examinations in at least 2 of the subjects. Another topic that I covered in that video. At least 2. So break down what it means when they say at least 2. If we are saying at least, the word at least really just means at lowest. So they're really saying the lowest amount of subjects they must be sitting for is 2 subjects. So at least, at lowest, we need 2 subjects. So this means that you can accept learners who are sitting for 2 subjects and who are sitting for 3 subjects as well, because the lowest amount of subjects they should be sitting for is exactly 2 subjects. So you can accept people sitting for 2 and people sitting for 3. Okay, so that's what we're going to do here. We're going to look for people sitting for 2 subjects or 3 subjects. So anything above and equal to 2. Okay, so let's look at these. Let us just look at, first of all, that these learners, there are 11 learners in total. How many subjects are they sitting for? They're sitting for 1 subject, maths only. Okay, they're not sitting for 2 subjects, so we can't include them. But what about 5? How many subjects are they sitting for? Well, this is the intersection of maths and tourism. So these learners are sitting for exactly 2 subjects. We're going to take them. And the 4, they are sitting for maths and geography. That's exactly 2 subjects. And the 3 are sitting for tourism and geography, exactly 2. What about the middle, the 2? These 2 learners are sitting for maths, tourism, and geography. That is a total of 3 subjects. So we will include them as well, because the lowest amount of subjects they must be sitting for is exactly 2. Okay, so that is what you're going to take. You're going to add these up, and they said the probability, right? Yes. So we need to express it as a probability, meaning you need to know what the sum of everything gives you. We can as well just find out that now. And you see that everything adds up to 40. So we know the total is 40. So the probability of, I'll just say at least 2, right, is going to be, we're going to add these 4 numbers, 5 plus 4. We can just add them up now. So that's going to be 5 plus 4 is 9, plus 2 is 11, plus 3 is 14. Okay, so that's going to be a total of, well, I guess we can show them the addition so that they know what we added up. 5 plus 2 plus the 4 plus 3, okay, all over 40. And this is equal to 14 over 40. And of course, that will just simplify to a simplified fraction. So that is going to be 7 over 20. Okay, you can do that. You can also just leave it like that. So that's our answer in that question. Moving on to the next question. Then 11.3 says, determine if the events sitting for examinations in mathematics and sitting for examination in tourism are independent And then you need to support your answer with the necessary calculations. Okay, let us understand what exactly it means for events to be independent. So independent events, how do they work? Well, if two events are independent, I don't want to waste too much time here, so I'm going to use the events they already gave us. If two events are indeed independent, then it means that in this case, we're talking about the probability of mathematics and tourism, right? That their intersection would be equal to the probability of mathematics multiplied by the probability of tourism. That's really what we need to look at. Okay, so notice this is the intersection of maths and tourism, right? Regardless of whether geography is included. It's just the intersection of maths and tourism. So that is inside here. And that adds up to what? 7. Okay, so the intersection of maths and tourism is 7 because that would be intersection M and T. Everything that is intersecting between those two. So these two together. Okay, and we're going to say that is 7 over what? That was over 40 that we had. And this should be equal to the probability of maths. So what is the entire probability of maths? This is not something that we actually have to calculate. We don't have to add everything because the entire circle of maths, probability of maths, is referring to everything here. Okay. And that's why we could safely say the probability of maths and tourism, that intersection is everything here. Okay, because there's no exclusion, nothing like that. So the entire circle of maths, we already knew what that was. They told us initially, and you can calculate it still. But the total number of learners sitting for mathematics is 22. So if you add it up, it will give you 22. So we know that is going to be 22 over 40 and multiply by the probability of tourism. Tourism would be the entire circle of tourism. Okay, did they tell us about that? Well, yeah, they did. So they said the total number of learners sitting for tourism is 16. Again, add them up, they will also give you 16. So that is 16 over 40. So we have 16 over 40. And now we just have to see whether this is true. So as you can see, 22 over 40 times 16 over 40 is 11 over 50. And as a decimal, that is 0.22. 7 over 40 is just 0.175. Okay, even if you round up. As you can see, they are not the same number. Okay, they don't equal each other. So they are not equal. And because they are not equal, we can therefore tell them that the events, mathematics and tourism, are not independent events. Okay, had they been independent events, that would have balanced out. They would have been equal to each other. Okay, but as you can see, they're not equal. Even if you round up, it's still not equal. Okay, so in conclusion, these events or the events are not independent. Okay, so that is it for question 11. And then we move on to question 12. Okay, so we are on question 12, and question 12 says, a company generates a 4-digit character code using 26 letters of the alphabet and 10 digits from 0 to 9. Okay, so they're using the full 26 letters of the alphabet and 10 digits. So the code is in the form of, so we'll have a letter and then a digit, then a letter and then a digit. Okay, so let's just keep that in mind. And the first question is 12.1. Determine how many different codes can be formed if letters and digits may be repeated. Okay, so the first one is quite simple. You're allowed to repeat. We have a 4-character code, and then we know that the first one must be a letter, the second one must be a digit, third is a letter, and the fourth is a digit. So we're allowed to repeat here. So we're looking at the entire 26 letters in the alphabet. We're allowed to use all 26 in the first character, the first spot. And then for the digit, we're allowed to use all 10 digits from 0 to 10. So we have 10 choices there. Okay, 10 choices we can use. Then repetition is allowed. So even if you use the letter here, you're allowed to use it here. So we have 26 options there. And again, with the digits, we are allowed to use the other 10 letters again because repetition is allowed. So this is just, 26 times 10 times 20. It's really just 26 squared times 10 squared. Okay, so you can find that on your calculator and that will give us the answer, which is exactly 67,600 codes that can be made with those restrictions or lack of restrictions. Okay, moving on to the next question. Then question 10.2 says, determine how many different codes can be formed if, and there are some criteria that we need to meet here. So first of all, they tell us that the letters D, F, I, Q, U, and V are not allowed to be used. Okay, how many of those? 1, 2, 3, 4, 5, 6 letters can't be used. Okay, we'll keep that in mind. Let me just put down the number of codes that we have already first. Okay, so that's in the order. And then we have the code may not start with a W or Z. That's 2 different letters it can't start with. So, and then they say letters and digits may not be repeated. And then the code ends with an odd digit. So you see that there are big restrictions on the first digits because they said it can't start with W or Z. And we also cannot use any of these letters. So remember that there are a total of 26 letters in the alphabet. We were going to be allowed to use all 26 here, but they said you can't use any of these 6. So minus 6 would be, we're down to 20 now. But then they say that the code may not start with W or Z. So the first one, we will not have 20 letters that we can use. We'll now have 18 letters that we're allowed to use. Okay, so 18 letters there. And then what would be, we can just deal with the letters first. If you're allowed to use 18 letters here, then how many letters can you use here? Remember that the letters or digits may not be repeated. So we were supposed to be able to use the full 20. But because one letter has been used here, we are down to 19 letters now. Okay, and now let's deal with the digits. So with the digits, we could start here, but there's a restriction here, so we can start here on the last digit. The code ends with an odd digit. Okay, so remember that the numbers they said we can use are from 0 to 9. So 0 to 9. Amongst these, which ones are odd? So we have 0 is not an odd number. It's an even number. Any number that can be divisible by 2 is even. And if it gives you a whole number at the end of the day, then it's even. Okay, so 1 is odd, 3, 5, 7, and 9. So that is 1, 2, 3, 4, 5. 5 numbers. So it means you're allowed to use 5 numbers here and the last digits. And then what can we use here? How many numbers can we use here? Well, they said that digits can also not be repeated. So if one number has been used here, just see it like this. You are allowed to use any of these digits here, right? But one has already been used here. So now you're down to how many? So you used to be able to use 10, but now you can only use 9 because one has been used here. So we started with the restriction so that we can actually properly control that. Okay, so there. And we can just find out what exactly this would give us. So 18 times 9 times 19 times 5. And that gives us a total of 15,390 codes. Okay. So that would be the answer to that question. That's the total amount of codes. And then we move on to 12.3. 12.3 says the company wishes to increase the number of 4-character codes formed in question 12.2 by allowing the letters D, F, I, Q, U, V to be used. Calculate the percentage increase in the number of codes that can now be formed. So at the end of the day, just find the percentage increase. So it's still this situation with all the other parameters that they already put down for us. But the only difference now with this is we are allowed to use those 6 digits they initially said we were not allowed to use. Okay, so let's just look at these carefully. Initially, well, I can't erase everything. Well, I don't actually have to erase everything necessarily, because the thing is that the digits are okay. It's the letters that change. So since we're allowed to use the 6 letters, these 6 letters, then let's look at the first letter now. How many letters are we allowed to use here? Remember that they already said the code may not start with W or Z. So because we can use all the letters now, we were supposed to be able to use 26 letters, but you can't start with W or Z. So that brings you down to 24 letters. Okay. And then the second letter that we're allowed to use is it would have been the complete 26, but they said no repetition is allowed. Okay, so that brings you down to 25 because one letter has been used here. So that will be 24 times 9 times 25 and then times 5. Okay, so digits didn't change, just the letters. And that is a total of 27,000 codes that we are allowed to use. Okay, so if we're allowed to use 27,000 codes, let's just look at the percentage increase. So to calculate percentage increase, you just take the new value that you have minus the old value that you had over the old and then multiply by 100. So for example, in like business, that's how you would calculate your price increase. Okay, the percentage of the price increase. So we times it by 100 so that we can get it as a percentage. Okay, so the new amount that we're allowed now is 27,000 codes, okay, that we can have now. The old amount of codes because of those restrictions was 15,390. So 15,390 all over 15,390 and then times 100. Okay, because you're really just comparing it to the old. You want to see how much it increased compared to the old. And then times 100. Okay, so let's see. Okay, so as a decimal, we get 75 point, and that rounds up to 44. So 75.44% increase. That would be the percentage increase. Okay, so that is it for this exam, grade 12s. And I will hopefully see you guys in my future videos.